everyone to tutorial multi-agent pathfinding. It's great that the number of attendees is larger than the number of speakers. So my name is Roman Barták and I'm from Charles University in Prague, Czech Republic, and the other speaker is Ronnie, returned from the Ben Gurion University in Israel. So what is multi-agent pathfinding? So let me start with a simple example. We have a graph like this grid with nodes describing locations and edges describing connections. And at some locations there are agents, robots, pebbles, whatever you want. And each of them wants to move somewhere else, to another location. And the task is to find a path for them. So the path may look like this. So in each step, each agent moves to the next location and so on. At this time, I believe this agent finally found its way to the goal, but others are still not there, so they need to continue. Now this one is there, and finally all of them reach their destinations. So the task is to find a collision-free path for all the agents till their destinations. This problem is called multi-agent pathfinding, but you can find it under different names like cooperative pathfinding, multi-robot path planning, pebble motion, and maybe there are other names. So in this tutorial, we will cover basically this type of problem. So first, I will go into more details to introduce more formally the problem and describe that there are some variants, some specific constraints that may or may not be assumed. There might be various objectives describing quality of plans, and obviously there are also applications. So I will just very briefly list some of them. Then we switch to the part where we will talk about how to solve these problems. So Ronnie will cover the search-based solvers. And after the coffee break, I will cover so-called reduction-based solvers that are based on reducing the problem to something else. And then Ronnie will again look to, let's say, a more practical part of the problem, and this is connection between the plans and a real execution of these plans, how to do it. And we will conclude with some open problems and challenges. So this is a tutorial, so feel free to interrupt us at any time and ask questions. The slides will be available later today or tomorrow on the web page that is accessible from AMA's website. And I'm also trying to video record it for those that prefer video. Okay, so let's start with a more formal description of the problem. So as I said, formally the problem is given by a graph. The graph can be directed or undirected. If it's undirected, we assume that the agents can move using the edge on both directions. If it's directed, obviously the agents must follow the direction. And the second part, as I already mentioned, is the set of agents. Each agent has some initial location. In this case, we have two agents with these initial locations, and each of them has also some destination location where the agent wants to go. So this is the input of the problem, and what we are looking for is a plan for each agent, and this plan may consist of two types of actions. One is moving to one of neighboring nodes, and the other one is waiting at the node where the agent is right now. And in most solvers and in many applications, there is an assumption that these actions have, let's say, uniform duration. So moving and waiting takes exactly the same time, which means if the agents are executing the plans, they are perfectly synchronized. So they do one action at one step. Okay? And plan is a sequence of these actions that starts for a given agent in the initial location and goes to the goal location or to the destination. Length of the plan is the number of actions in the plan until we reach the goal state. It's a bit tricky to define it precisely. It's not the first time when the agent reaches the destination, because the agent may be in the destination, but it may need to leave it because another agent wants to go through the destination. So it's exactly the last time when the agent enters the destination, and since that till the end of all the plans, it's not going away from this. And you will see it in some examples later. Okay? And the task is, as I said, finding a plan for each agent such that the plans are space and time collision free, so they do not collide. The agents are not at the same node at the same time. So this is the example that I showed before. We have a graph, two agents, they want to go to the other part of the graph. Obviously there is a bottleneck in the middle, so they cannot go in parallel. One of them needs to go first, so it may look like this. The blue agent is waiting, the red one is going, and now they continue to their destination. So the red one is already there, now the red one is waiting, and finally the blue one reached the destination. Okay, so this is how the plan looks in a sequence of actions. So you can see that the plan length for the agent 1 is 4 steps, for agent 2 it's 3 steps, the last time is just waiting, so we remove all the waiting actions at the end. So this is the, let's say, initial setting for the multi-agent pathfinding, but there are some additional constraints that I will describe. Obviously, we can define some trivial conditions when a plan may exist. For example, if two agents are at the same node at the beginning, there's no chance to find a collision-free plan because there is already a collision there, right? Similarly, if two agents have the same destination, it's not possible to find a collision-free plan because at the end, they need to be both there. And unless we remove one of these agents, there is always a collision, right? So if there are the same destinations, it's not possible to find a plan. The next condition is useful in some settings, and it says that the number of agents must be smaller than the number of nodes. Obviously, if the number of agents is larger than the number of nodes, then the first condition is not satisfied because two agents must be at the same location. Even if the number of agents is equal to the set of nodes, if we do not allow swapping, and I will cover it in a minute, it's not possible to do anything because the agent cannot move anywhere. Okay, so these are some trivial conditions. So I mentioned the swapping. So let's assume that we have a problem like this one, and the blue agent wants to go from the node 1 to node 2, the red one from 2 to 1. So the plan may look like this. Okay? It looks like it's a collision-free plan because at any time the agents are not at the same node at the same time, but obviously we can see that they share the same edge. So if this edge has capacity 1, so it's not possible to go in this edge in both directions, we should forbid such swaps. And this is quite typical in many settings for multi-agent pathfinding that swapping agents is not allowed. So in this case, we can find a plan that looks like this. The red one needs to go away, so the blue one is now in its destination, but it needs to free the destination for the red one, so the red one can go to its destination and the blue one can go there. So now you can see that even if the agent 1 is in its destination in step 1, the plan length is actually 3 steps because this is the last time it reached the destination. And for agent 2, it's also 3 steps. Okay? So the no swap condition basically says that if agent at some node I wants to move to node J, it's not possible at the same time that the agent at node J moves to node I. And this is somehow hidden assumption that almost every algorithm assumes as the requirement. But let's now look at this problem from a slightly different perspective. I will replay the plan that I showed you before with no swaps. So it looked like this. The red one is going there, the blue one is and you can see there was a small crash because one agent was slightly late. Okay? So in this case, what happened was that the agent forms so-called trends. The agent starts moving to a node, even if that node was occupied when the agent starts moving, but the hope is that when the agent reaches the destination, it will be free, right? which was not the case here. So we call it a train because there are like agents going one after another one. It might be desirable in some applications, like, is it called carpooling? So if you have many cars following each other in a highway, but it might be also dangerous, as we saw. So sometimes we may forbid the trains. We may say trains are not allowed. It's possible to find a plan in this case by just inserting some wait actions, so there is a gap between the agents. Okay, so this is how the plan may look like. So the agents are waiting. Okay, so a train is forbidden if we do not allow agent to move to a given node which is occupied right now. So we allow only moving to nodes that are free when we start movement. Okay? And to show more practically what's the danger of trains, the major problem is that if we have a train, then the agents are close to each other. And this might be okay at the abstract level, but it may not be okay at the execution level. Okay? So if you look like this, we can see this is a perfect train. So now they are going like in a highway, but it may happen that some agent is slightly late, and it may lead to collision. Okay? So this is the first minor collision, but still they are able to restore from it. But now a major collision appears, and this agent is simply lost. It cannot continue. Well, it could maybe, but it's now unsynchronized. Yes, question.
Yeah, Roman. It's not a question, it's maybe a kind of remark. I believe that it's not about the train thing here. It's about the size of the, like the actual size, the metric size of the edge and the agent. So if you just put the vertices a bit actually like, which is like square root of radius doubled by 4, divided by 4, there won't be any problems in this example with the train.
Definitely, yeah. So it's related to crowded area, right? So if the agents are very close to each other and the trains are also, the agents in trains are very close to each other, then it's danger. If we make a larger gap between them, it may not be a problem. So that's why I say that sometimes trains might be desirable because we are using the space that is available. Sometimes in crowded areas like this one, where the agents are big and the distances between nodes are small, we may need to assume that trains should not be allowed because the chance of collision is higher. So yeah, obviously this is the difference between the abstract model, just nodes and edges, and reality where we need to assume physical distances.
Yeah, my point was that it's not the train which is the reason of collision. So train is actually good. It's the distance between the nodes. Because if the distance is okay and you assume perfect execution, it's okay.
If you assume perfect execution.
Yeah, but so the source of the collision is imperfect execution and the distance between the nodes, but not the train. Even from theoretical point of view, it's like not the train. The source can be either imperfect execution, which always happens like in real robotics, but even if we assume that we have this imperfect execution, there is also one more source of collisions, but it has to deal not with the train thing, but with the distance between the...
Yeah, so we can define the train where the distance is larger, as you will see in a moment, right? So it's a formulation of the train at the abstract level that the node should be free when you are going there, and it's because of the size, right? But we can form trains which have small gaps between them, which is exactly what you are speaking about. So it might be about different formulation, right? So yeah, so we may need to introduce more space between the agents. That's the idea. And that also led to a notion that is quite new. It's called robustness. So the idea is that we would like to generate plans that are robust to delays of agents. So if some agent is slightly late, the plan should still be executable. So K-robustness means that if the agent wants to move to a given node, that node should be free for the last K steps, which prevents the agent to collisions with agent that was there before for k steps. Okay, so this is the same example as before, but we just required one robustness. So if you look at it, it looks like a train, but there is a gap between them, right? So the train is no gap at the level of nodes, but still they follow each other like a train, right? So it's a formal definition of trains that the node should be free before we go. And in this case, it's actually working, so there is no collision, and it's corresponding to what you said. It's enough if there is just larger gap between the nodes. Okay, but it may not be possible always to define it because, for example, like these lines to be close to each other, right? So that's the reason why we may forbid trains of a given with a given distance between the nodes. But then the system may use the trains like this one. So it's actually working. Okay, so both of them reach the destination. So this was an example of one robustness. The node must be empty before we go there. And actually, the one robustness covers the node swap constraint. It also covers the node train constraint. Okay, so there might be other types of constraints we may introduce, like we may never return back to the node that we visited before for some reason, so no plan, no path as a cycle. Or two plans are not allowed to visit the same location. For example, we would like the passes to cover the area rather than to reach the destination as far as possible. We may forbid waiting, like if you have an airplane, I mean the fixed wing airplane, it's not simply possible to say, okay, stay here because the airport is closed, so you need to move all the time, so we may forbid waiting. In the direction of traveling salesman problem, we may require the agent to visit some locations before reaching the destination, and so on. So there might be many other side constraints we may introduce to the problem. Okay, so far I was just talking about feasible plans. So what does it mean that the plan is correct? But obviously we are looking for good plans. So now the question is how we can measure quality of plans. And there are two major objectives that I use in the multi-agent pathfinding that are being minimized. The first one is so-called make span, which is the distance between the start of all plans and the end of all the plans. Or in other words, it's the maximum length of all these plans that run in parallel. And the second typical objective is so-called sum of costs, which means it's a sum of lengths of plans, or sum of end times. Why by end time we mean the time when the agent reaches the destination. It's not leaving it anymore. Okay, so these are examples of plans. So if you look at it, what's the make span for these plans? Based on the definition.
The make span for which plan?
For both plans are part of the solution. So the make span is measured for all the plans together.
4.
It's 4. And what about the sum of costs?
7.
7, exactly, right? So it's 4 because we need 4 steps for both agents to reach their goals. And the sum of cost is 7 because the agent 1 needs 4 steps and the agent 2 just needs 3 steps. The last 8 is not included in sum of cost. Okay, so the make span is 4, sum of cost is 7. But maybe it's not obvious, but these two objectives, if we optimize one of them, it does not mean that we get the best plan in the other one. Okay? So for example, for sum of costs, we may need to introduce plans with longer make span to minimize the sum of costs. So they are not identical in terms of optimization. Okay, a few words about the complexity of the problem. So finding optimal solution for one agent is easy. We can use like this algorithm, whatever. If we are looking for suboptimal solutions for the multi-agent pathfinding, and we know that there are at least 2 empty nodes, that it's also solvable in polynomial time. There are several algorithms like push and rotate. But the solutions produced are not that good in terms of the objectives like the make span or sum of costs. If the agents have joint goal, meaning the agents have a set of goal locations where they need to finish, but it's not specified where exactly each agent should be, then this problem is also tractable. It can be solved in polynomial time. But if we use the optimization version of multi-agent pathfinding, it's NP-hard. So if you want to find the best plan, minimizing make span where each agent wants to reach its destination or sum of cost, it's hard. Okay, so now we are going to some applications where this abstract model can be used. Some of them are abstract applications like puzzles. I guess all of you know the Lloyd's puzzle. So it's an example of multi-agent pathfinding problem. Each tile is an agent, so it has a location. There is just one empty node here. And actually in each step, exactly one agent is moving. Right? So it's a type of very crowded multi-agent pathfinding problem. Obviously, we can find these problems in warehousing. So there are many agents that wants to go to the destination. This is an example from the Kiva systems, now Amazon Robotics. Perhaps not that straightforward applications are from chemistry. It's called lab on the chip. And where is the pathfinding? Well, the idea is that there are some small droplets that are moving between locations, and we need to carefully plan passes of these droplets. So I guess they pick up some substance somewhere and move it somewhere else where it's evaluated and something like this. So it's an example of multi-agent pathfinding. Okay. Obviously, computer games. So if we have games where we have many small agents that are not controlled by humans, like an army that needs to be moved somewhere, we would like this move to be reasonable, smart. So we need to plan movement of these agents there. And this is another nice example of multi-agent pathfinding. Let's say intelligent junctions where we have many agents that want to go through the same area. Okay, so it's a problem that has an abstract part, but there are many applications that can be solved using these algorithms. So speaking about the algorithms, we will cover two types of algorithms. The first one is search-based. It could be, for example, the classical state space search like the A*, where state describes locations of agents, and transition means adding action to each agent. But there might be search techniques using different search spaces, like the conflict-based search, where the search space is defined not by the locations of agents, but by conflicts. So we are trying to remove conflicts between passes of different agents. So Ronnie will cover this part in a few moments, and after the coffee break we will go to what's called reduction-based techniques, or compilation-based or reformulation-based techniques that are based on the idea of translating the problem to another formalism like Boolean satisfiability, CSP, mixed integer programming, ASP, whatever. Okay, so that's the end of the first part. Any questions about?
Yes. Are we focusing on central solutions, or should we
Yes.
speak about distributed?
Right now we will be covering the centralized approach. I guess
Okay.
Ronnie will cover only the
Yeah,
centralized,
yeah.
and me too. So it's about centralized approach where all agents register their demands, we centrally solve it, we generate the plans, and then we distribute them. So it's not about distributed.
Yeah, we can talk a bit about that at the end.
At the end.
If you would like.
Okay. Good. So.
Yes. Thanks. Thanks, Oman. Okay, let's say that this one is mine.
Yeah.
Okay. So hi everyone. Just so I'm aligned. So how many of you have known about multi-agent pathfinding before? Have read about it a bit in the past? Okay. Good. Good. Okay. So then I can go a little bit deeper if needed. But again, the idea, as Roman said, is that this is a tutorial, this is a discussion. So, well, not a discussion, but it's open for discussions. So please ask if something is not clear. Also, I will say before I start that maybe you have noticed from my few sentences now, I speak fast. Please stop me. It's okay. Tell me slow down, and I will slow down. Okay, good. Then I'm Ron Stern from Bengal University, and I'll talk about search-based solvers, which combines two things that I like a lot: search algorithms and multi-agent problems together. And the idea is that, of course, we want to solve the multi-agent pathfinding problem, and let's see how it works.
The big one is.
So cool. We want to solve it not for 2 agents, but for many. And fortunately, search-based algorithms can do that, even optimally, in some cases, for more than 100 agents, which is pretty cool if you remember that Roman just said it's NP hard. So, but why search-based algorithms? So the reason for that is that, well, search-based algorithms have been used very successfully for these 2 types of problems, right? For single-agent pathfinding, like A*-based algorithms are very good at solving these kind of problems, and also for tile puzzles, right? This is the classical setting for A*. And as Roman said before, tile puzzle is one extreme example of multi-agent pathfinding, where the number of agents is 1 minus the number of locations. And this is also a multi-agent pathfinding problem with single agents. So if search algorithm worked well for these 2 cases, right, then hopefully it would work well also for any number of agents in between. And I use K as the number of agents, if that was not clear. Okay? Okay, so just like a very, very brief reminder. I know most of you, all of you, know very well search algorithms. But just as a reminder, we're talking about the classical search setting. So you have a start state. This is the example of a single agent search. You have a goal state. And how do you move between states? You have some operators. So what are the operators in single agent pathfinding? Move. If you have only 1 agent, there is no point in waiting. You just move. Right? And then search algorithms want to know which kind of state to look at that will reach us to the goal. So we want a sequence of states that will get us from start state to goal state. Classical search, everyone knows that. The problem is that we don't know which one would lead us to the goal. But the way search algorithm work, what is the basic thing that search algorithm do in a search space? They expand nodes. Right? And what does it mean expand? You apply all operators and you see who are the next states. Really basic. And we also know that one of the main factors that affect the complexity of such algorithms is the branching factor. How many operators do you have? Very, very, very roughly, not exactly correct, but if the branching factor is B and the domain is exponential and there are some other constraints, then we are exponentially in the depth of the solution, which is again very well known. But the key thing is that the branching factor, the one that's in the base, that's very important. Okay, I will get back to that later. Okay, and then such algorithms, the way that they work well is that they know what kind of states to choose to expand first, using heuristics and other values. Again, this is very well known, right? Anyone is good? Okay, so what we'll do now, I try to show you search-based algorithms that cover these 4 combinations. So I'll show you optimal search algorithms that are incomplete and one that are complete, and optimal search algorithms that are incomplete and complete. Actually, this one I won't show you. Okay, so no incomplete optimal, only the other 3 options. Okay, so let's look at the first attempt. So this is Silver's famous work on cooperative A*, and the idea is very, very, very simple. It's amazing that it's only been invented 13 years ago, because at least the basic approach is very simple. You take every agent, you plan for it separately, and every time an agent plans, it tries to avoid the previous plans of the other agents. Okay, so let's see how it works. Very simple. So let's say we have 2 agents, blue and red. The red wants to go to the White House for some reason. And so we start to plan for the blue one first. So blue. Okay, now it's red, that's okay. So you plan for the blue one, and now you plan for the red one, but the red one tries to avoid the other plan. So it goes here, and what will it do now? If it wants to avoid the other agent's plan?
Fail.
It can fail, it will be sad, but it tries to avoid it, so what can it do?
Wait.
Wait, right, so it can wait it went to avoid, so it can wait 1 second or 1 time step and then continue on to the goal. Okay, again, and this carries on to all the agents. Again, a very, very simple algorithm, at least the basic one. So now, but let's try to analyze what's going on. Okay, so the first agent, the red one, it ran a classical search problem, right? It had 4 possible moves, and its search space would look something like this, and so on. Very, very standard problem. So if you look at it, the state is the agent's location in the first agent's path. The number of states then is 20 if you look at it, in this case. And what's the branching factor for the first agent? 4, right? It's written there. Okay, so because it has 4 moves. Now let's look at the second agent, the blue one. Yeah, I took a little bit slightly bigger grid so it will be easier to show things. So the blue one also runs as a classical A* search, more or less. So it starts and it looks at all its location and its subsequent location and so on, but then something is missing, right? The blue agent needs another capability. What does it need to be able to do? Wait, good. So it has another one, right? So it doesn't have only its 4 cardinal location, 8, 12, 14, and 18. It can also stay in its own location. Okay, you don't see the number, but you can imagine that if it's between 12 and 14, it's 13, right? Okay, so we need this option as well. Okay, so its branching factor is not 4, it's 5. Not huge, but let's look at the search problem and what is the state in this setting. So previously a state was the location of the agent. What is the state now?
Location and the time step.
Location and time step, right? Because we need to differentiate between being at 13 at time step x and at time step x plus 1. So the state is a location time pair. So this means how many states do we have in this case? We have 20 grid location. How many states in general?
It depends on how many time steps do we want.
Exactly. So it depends on how long it will take us to get to the goal. If we put that as it's a maximum value, it will be number of states times some max time. Okay. So this is a larger state space. And the branching factor, how much would it be?
5.
5. Okay. Again, I'm starting easy, so the hard question would come later. Okay, so then a nice way to look at this search space is not like this, but actually like this. So it's a three-dimensional search, and the z-axis, the depth, is the time. Okay? And what's important to see is that if you look at the gray cubes, these are the locations already taken, or time location pair already taken by the previous agents. So every agent searches in this cube, avoiding the time per location used by the other agents. Okay. Questions? Good. Okay, so this is the algorithm. Again, you have some reservation table which reserves all these gray locations, the places that were already taken, and each agent finds a path avoiding these gray locations and adds its path to this reservation table. Okay. Good. So, good thing is this works wonderfully for a lot of agents. You can see here the x-axis is the number of agents, and this is the number of cases solved. And you can see that at least one of the combinations, I won't go into different lines, but one of the high combinations is a variant of this approach. It works well for many agents, which is nice. If you think of the complexity, how much is it? The search space itself, it's the number of locations times the number of time steps. Okay, so it's only polynomial in the grid size and the max time. Polynomial still, that's not super hard in many cases. Is the solution sound? Do we get a plan where the agents do not collide and get to their goal? What do you think? Do the agents reach their goal? Yes, right. Every agent avoids the other agent that were before it. So then they eventually reach their goal. So it's sound. But the question is it complete? So complete, what I mean by complete, I mean that if there is a solution, the algorithm will find it. Sound means that if there is a solution, if it outputs a solution, then the solution is correct, no collisions. Complete means that if there is a solution, it will find it. Okay, so is the solution complete or is it optimal? No. What do you think? No, clearly not, right? So let's see a very simple example. Okay, so blue wants to go to blue, red wants to go to red, and let's say that the first agent that plans is the blue agent, so it does this. So this is its plan. Go to the blue house and then you're at home. Now if it's the red agent's turn, it can never get to its home. Right? So then there is, so the solution here is not complete, of course not optimal, and this problem is solvable, right? How do we solve it? One of them needs to go up here, another one will go there. It would never define this with this algorithm. Okay? So not complete, not optimal. And why is that? The goal location blocks one of the other agents. This algorithm, again, simple, working well in many cases, but it has other limitations also. It's an all or nothing approach. You can't move until everything is planned, which is a limitation in many cases. Actually, so this limitation, they have some way to overcome it to some extent, which is called window hierarchical A star, cooperative A star. I won't go into a lot of details there, but I will say very, very briefly that they plan for a window of k time step or n time steps, and after that, and we do the replanning every such iterations. So there is some way to make this algorithm work to be more anytime-ish. Okay. And the last limitation of the algorithm is that the ordering of the agents is crucial. And how to set which agent to start from, that's not very clear. There is no good guidelines on which agents to choose first. There is some work on it by Bnaya and Fellner a couple of years ago, but there is no definitive answer. This is the correct way to order the agents. So this, on the upside, there's room for future work in heuristics, but on the downside, we don't know how to do that very well. And it has a huge impact on the performance of the algorithm. Questions so far? Yes?
Situation where the two agents have the same goal
Yeah.
is also not solvable.
Yes, but the situation where two agents have the same goal is not solvable in general.
Yeah, but that's a constraint generally. You will not speak about.
Yes,
Okay.
but I will say that in some configuration of the problem, where when the agent reaches the goal, it disappears. If that's the case, then we can solve it, and we do have some work on that. Very preliminary stuff. Yeah, more questions?
It's not a question, Ronnie, it's just a remark that there is actually a few works mainly in robotics community which do pay attention to this setting, and there is like some preliminary work on how do you need to like choose which engine go first, which engine goes second.
Yep.
They use like the simple heuristics. Like for example, if you wish to minimize the make span, you should assign highest priority to the longest first. I mean, like you just. So and it's not the question, it's just the remark that the ordering is definitely the key, and there is like a bunch of.
Yes. So this is one example. I know that there are more.
Yeah,
This is for week 14, but yes, there are more works.
Yeah, there are more, and they are more, like 10 or 12 even years ago they were published.
And the reason is because the algorithm is so relatively easy to implement, so it works nicely. So that's why people have been paying attention to it. Okay, good. So let's move to the next quadrant. So we have a suboptimal incomplete algorithm we have now. It's cooperative A star and its extensions. Let's look at complete solutions. So can a multi-agent, in general, can a multi-agent pathfinding algorithm be complete and also efficient, meaning polynomial in something? What do you think? This is a quiz. You've seen this before, it's a couple of slides ago. What do you think? Yes, no?
No.
No. Okay, so actually, the answer is yes. Okay, so we can look at the multi-agent pathfinding problem as a puzzle, and people actually have done that. But don't feel bad. It's okay, because there was a line of work that, like you, have forgotten an old paper that solved this possible. So that's okay. So in specifically, multi-agent pathfinding is very related to a very classical puzzle, the pebble motion problems, where you have pebbles and you need to move them from one block to another to some target location, and you can see the mapping, right? Even Roman said that 15 minutes ago. Okay, so each agent is a pebble, and you need to move each pebble to its goal, and you cannot put pebbles in one hole. And surprisingly, this puzzle can be solved polynomially in time that's cubic in the graph size. So there is a polynomial solution. But so why do we have a half day of tutorial if something is solved in polynomial time? So you're not here just to waste time. The solution is very, very far from optimal, and the formulation is very complex. So it's hard to implement. More importantly, you wouldn't want in many cases to use the solution because it's so long. Nevertheless, it's possible. And again, I told you not to feel bad. So all these works and many others have been working on complete polynomial time solvers for the multi-agent pathfinding algorithm. And only in 2012, there was a paper, this problem has been solved in 1984. Okay, so this happens sometimes in academic life. I'm not saying that these works are not useful. They are, because they often do find faster solutions, not faster, but better solution than the Cohen-Hauser algorithm. And just to give you a hint of how they work, all of these algorithms follow a kind of procedure. So it's not unlike how the macro approaches for solving the Rubik's Cube. So do you know how to solve? Like, who knows how to solve the Rubik's Cube by hand? Only one? Okay, so homework, don't do that. But there is an algorithm to do it. Not a certain algorithm to run the exponential, something that a human brain can do. there is some macro operators, or how to move each qubit to every location. Okay? And there's also other approaches which also can work. but let me highlight several of the examples. So here's the push and swap algorithm by Luna and Beckeris. So the idea is you have two operators. You have a swap operator. So you see agent 2 and 3. So the operator is how do you switch the location. Okay, so 3 will move down, 2 will move to the right, and then they go back. So you have one operator that does this swap. And another operator is push. You take an agent and you move it all the way to some location. And the push and swap algorithm uses these two macro operators and applies them together to get the solution. So very, very roughly, I won't go into the detail, but you order the agents according to some order, you push each agent until it reaches a goal, or it is blocked by another agent. If it's blocked, then swap. Again, there are more details there, but this is the high level of the idea. Again, this is polynomial time. It works in every case where you have at least 2 open spaces. There's a code downloadable if you want to actually run it. Another example is by Pavel Surinek. It's the B-box algorithm. This is another algorithm that's complete. Again, not optimal. It works for every graph that is biconnected. And the idea is that you take the graph, you do an ear decomposition of it, which basically makes it like this, with a cycle and several ears. And then from that on, you take every agent and move it to its location by rotating the different ears. Again, more details there, but this is the high-level idea. Another example also is the FAR algorithm, which works for every case where you have wide corridors. So again, there was a line of work on how to solve this problem. All of these works share several properties. They are all running polynomial time. They are complete in some large classes of multiple patterning problems, and they do not guarantee anything about the solution quality. Okay? Questions? Good. Okay. So we filled 2. Now we have the last one that I want to talk about in this session is the optimal and complete set. So we want to find an optimal solution. So let's go back to the search formulation and try to exploit that to get optimal solution, because we have a lot of theory and literature on how to use heuristic search algorithms to get optimal solutions. Okay, so the single agent case, we already talked about that, and we already talked about what will happen with the second agent adds, so the state space becomes this location time pair, but we saw that this did not give us optimal solution, and one of the reasons for that is we didn't know how to choose which agent to start first. So if we look at it more generally, the more general way to look at the search problem is this state would not be a location time pair, because this doesn't say which agent, but it would be the location of all agents. So every state would be a location-location pair. Okay, so the start state would be the pair of the start state, and every action is to move both agents. Let's see how it looks more concretely. Okay. So every agent, the number of possible move it has is 5. It can move and wait. And they move together. So the possible action in every time step is the product of the both of the two actions. Okay, so in every time step we have 25 possible movements we can do. Okay, do you see that? Is that clear? Okay, so for example, in one time step, red can move to 6 and blue can move to 12. That's one option. Right? And another option is red moves to 6 and blue moves to 18. And so forth, so we have 25 actions. Okay? And it looks like something like this. Okay? So start is the most start location, but from moving onwards, it's all possible cross products of locations. Good. Okay, so this also, and now we have a classical search problem. We can solve it. We can use heuristic search algorithms and solve it as is. The start state is the start of both agents. The goal is the pair of goal locations. We have actions. We have search tree. Wonderful. Okay. The only challenge is that now the number of states and the branching factor become exponential in the number of agents. Right? So we had 25 moves with 2 agents. With 3 agents, how many moves will we have?
3.
3. 125. And this is the branching factor.
5, 5, 5, 5.
Yeah. So the branching factor it will be exponential in the number of agents, and this is very bad because we know that the complexity in worst case ignoring heuristics is exponential where in the depth of the location. So, and the branching factor is on the base. So it will be almost doubly exponential in the number of pages, even longer. Okay, so it becomes a very hard problem. So now I go back to the same question I asked you before. Can we find a multi-agent pathfinding algorithm which is complete, efficient, and also optimal? This is again a quiz because you've seen that before. It's okay, I'm just.
No.
No, okay, no. So the answer is no. And why is that? Informally, the state space is exponentially in K, branching factor is exponentially also in K, and more formally, as Roman said before, it's NPR. So, okay, but you know, so this is an AI event, right? And we all know that in AI we see NPR and laugh, right? NPR, we can solve that. And for example, solving optimally the tile puzzle is also NPR, and we do have a bunch of algorithms to do that quite efficiently. So I go back to what I started with. Can we use the techniques we used in classical search algorithms, classical search problems like pathfinding and tile puzzle, and use them here? And the short answer is yes, and the long answer is there are some new techniques that we need to invent. So this is really what I'm going to talk about as we continue. Okay, what I'm showing here is that the x-axis is the number of agents, y-axis is the percentage of cases where we were able to find an optimal solution, and what you can see is that we are able to solve in a lot of cases for more than 75 agents, and by solve I mean find a solution which is provably optimal. Not likely optimal, but guaranteed to be optimal. Okay, and all of these are search-based techniques I will cover next. Okay, questions so far? Okay, good. Okay, so I'll start with techniques that are very based on the classical A-star algorithm, which I assume you all know, and then we'll move to more, let's say, domain-specific and non-A-starish approaches. Specific ICTS and CBS. Each of them is a family of algorithms, so there are improvement and improvement. I will try to cover the basic and a little bit of the more advanced stuff as time permits. Okay, so let's start with the core of the problem, because what I showed you before, we had two things that made this a hard problem: the size of the search space and the branching factor. And to be honest, the main problem, so both of them is a problem, right? But there are many search algorithms that are specifically designed to solve problems that have a very large state space. But the key problem in this case is actually the branching factor. And let me try to explain to you why. Okay, so A star, so again, everyone knows A star, right? Someone doesn't know? Okay, good. So A star expands nodes, and it gains efficiency by choosing which node to expand and which nodes not to expand. Okay, but there is at least one node that it must expand. Which one? Which node A star must expand?
The one that minimizes the G value plus H value.
So you're right, it needs to expand every one with F value smaller than G plus H, but even to make it simpler, the root of the node, the start state, it must expand it, right? No matter how good is your heuristic, you have to expand the start state. Maybe your heuristic is wonderful and to tell you how to go exactly to the goal later, but the start state you need to expand it, right? Good. So let's think about how much it will cost us to expand a node in multi-agent pathfinding. Okay. So what is the complexity of expanding a single node in a multi-agent pathfinding problem with 20 agents? Okay, so the branching, right? So the branching factor, right, which is 4 and weighting, but to the power of 20. Okay, just a curiosity. This is how the number looks like. It's large. So even if you have a wonderful heuristic and a wonderful heuristic search algorithm, you're still in a problem. Okay. So what to do? So the first major conference I went to was AAAI 2010, and as every student knows, the thing you do to get money is I volunteered to stand in a booth and give the tags and all that. And fortunately, beside me, I sat this guy, Trevor Stanley, and I told him, what you're working on? He said, I'm working on multi-agent pathfinding. And I said, oh, cool, I'm also working on that. It was very nice. We had a lot of hours of fun. And the thing that he invented there, I like it because it's simple and elegant and working nicely. So he had two nice ideas. Maybe he had more relevant to our discussion. Probably he had more, he's smart. But okay. But for our discussion, two very nice ideas. The one we call it's called operator decomposition. The idea is that we add this intermediate layer. So again, this is the regular search space. You start with the initial location, okay, so I and A, and then you have these 25 options of where to go. Okay, this is what we covered so far. And what Trevor suggested is that, okay, instead of looking at all possible 25 combinations, add an intermediate layer. So add a layer in between, and in that layer, only one agent moves. Okay, so again, just to clarify, these are the real states. That one with dotted. Okay, so from A and I, forgive me for the pun, you can move to DF and all that. But in this intermediate layer, I only look at the motion of the red agent. So I assume the blue agent stayed at its location, so stayed at I, and only look at that agent's location. So if you think about it, these intermediate states, they don't represent any real state. Why? Because the agents are in different time steps. So here, for example, in this state, the red agent is the time step 1, but the blue agent is still in the previous time step. And then the subsequent layer is moving the next agent. Okay? Good. Question on that? I think for me, when I first saw it, the first question for me was, okay, what did we gain? We got more states. This is usually not a good thing in such algorithms, right? We want to have fewer states. Okay. So what did we gain? And the gain comes from having a heuristic. So now if you have a heuristic, you can apply it also to the intermediate states. And this way, you can prune off branches before getting to the full state. So let's take this argument to the extreme. If we had a perfect heuristic, we could expand only the first layer, immediately not expand all these guys, and go straight to the goal. Okay. So this gives us a way to partially expand some of the nodes. And this is crucial for us because expanding a node in multiple pathfinding, that's horrible. That's exponential in the number of agents. Okay. Good. So, operator decomposition, OD, is an abbreviation. Its pros, the branching factor is reduced to 5. Of course, there is a price to pay. The branch factor is smaller, but the solution is deeper. But because we added these intermediate layers, the big pro is that we can now use a good heuristic to solve the problem, which we could not before. There is also, of course, if heuristic is not so good, you don't gain a lot. It's not horrible, because what usually counts the most in such algorithm is the last layer, and that does not get bigger with OD. Okay. Questions? Actually, this OD is a special case of a more general algorithm called enhanced. Yes.
I'm guessing you might come to that, but how do you choose which one you should move first?
Yeah. Okay. So we're running A star, at least in this setting. So an A star uses the G value, the number of steps so far, and the H value. So what's the heuristic? Okay. So this is a good question. So in single-agent pathfinding, in grid world domains, without any sophistications like Manhattan distance is usually used, but in this case, because what costs you the most is not the single-agent pathfinding, but the interaction between them. So what's commonly used is to compute the shortest path from every location to every goal up front, and then have a perfect single-agent heuristic. And then the multi-agent heuristic is the summation over that heuristic. So for example, I'll take a look at this state. It's both agents moved, so its G value is 2, and the H is the shortest path from D to its goal, so D, yeah. So 1, and from F to its goal, which is 1 also, so the heuristic would be 2, because they have to have at least 2 more movements to get to the goal. But yes?
I don't think that answered my question, because if you move to the next slide, you told us about the intermediate layer where you move one agent first. I was asking how you decide which that first agent is.
Okay. So now I understand. So good question. There is no answer for that. So how to assign which agent to start first? That's a wonderful question, and people have not studied how to do that. So here it was just like some random ordering, and I think it would make a significant difference, because then you could prove first if there is some agent that does some move that's very goes against the heuristic. Yeah. Okay, good question. Yes. So this OD is a special case of a more general search algorithm called enhanced partial expansion A star. And the idea is that when you have a large branching factor in general, it helps if you have some kind of function that tells you which nodes to generate first. And again, I won't go into the detail, but imagine that you have a root node and you have a bunch of states that you can generate, but you have some function that tells you only this state has an f value has the smallest f value. And enhanced partial expansion A star knows how to use this kind of like operator selection functions to search more efficiently. Again, I won't go into the scope, but I just mentioned that there are some locations. There is a tutorial on heuristic search on Friday, so if that's interested, you're welcome to. It will be also covered there. Okay, questions? Good. Okay, so now here comes the second nice idea by Trevor, which is called independence detection. And I like this idea a lot because, first of all, it has a lot of huge impact on performance. Secondly, it's elegant. And third, it can go on top of every other multi-agent pathfinding algorithm. So it's a framework in some sense. And the idea is like this. So look at this three-agent problem. So we have agent 0 needs to move from S0 to G0, agent 1 from S1 to G1, and agent 2 from S2 to G2. Okay, so this is a three-agent problem, in theory. But if you look at it closely, what's very clear from this problem?
The agent 2 is kind of independent.
Yeah, so these agents need to synchronize this some way, but this guy don't really need to talk to them. Okay? And detecting this is very important because you remember that everything is expression in the number of agents. If I can tell you, if I can identify that this is one problem with k equals 2, and this is another problem with k equals 1, this will be exponential speedup. So this would lead to an exponential speedup in the performance. Okay, so how to do that? The simple detection algorithm works as follows. You take each agent independently and solve it, ignoring all other agents. Then it might happen that agents will conflict, right? Because it's a multi-pathfinding problem, they might conflict. So if agents conflict, you merge them to one group and then you resolve them again together. This is it. Very simple. Again, you solve optimal each agent. If there is a conflict, you merge, you resolve, and then it's done. Let's see how it works here, for example. Sorry. Here, for example, so agent 0 would plan this path, agent 1 would plan this path, and agent 2 would plan this path. Now, which path collide? The ones of agents 0 and 1. So they will be merged together, and we will solve them as if there are two agents. So we will solve a two-agent multi-pathfinding problem, and the solution would be something that where they do not collide. So, for example, S1 moves all the way here, and then it moves all the way there, and S2's solution would not conflict with it, and then we'll have a complete solution for both agents. And the nice thing about this algorithm is that it's probably optimal. So you have the output is something that's complete and optimal and exponentially faster. Okay, but this does not solve all problems in the world, because in some cases like this one, still the agents collide and we need to solve them somehow. So for example, if we run the algorithm here, so let's say we had agent 0 find a path, it found this one. Now, which path agent 1 should find? How many options does it have? Agent 1. Agent 1 now plans ignoring agent 0. Like how many options it has?
It has lots of options.
Lots of options, right?
There is a lot of symmetry.
I was hoping for that action. It's not. It can pass to this, but it can go this and this and this. There are a lot of options, but it doesn't know. So let's say, unfortunately, it shows this path. Then what will happen if we're running independence detection? We'll merge them and solve them as a two-agent problem. But if you look at it closely, that's just bad luck, right? Because if this agent would think a little bit, it would know, okay, it went here. I should choose this one, and then there will be no collision. Okay. So now you move. I hope you're seated. This is not too simple in the detection, but to independence detection. It's not simple. Okay. It's not simple, and the not simple part is very simple also. It's just saying that if you have this collision, each agent tries to replan again, but avoid the other agent, but importantly, while maintaining the same cost. So the idea is that agent 1 planned this this colliding path, it has the cost of 1, 2, 3, 4. It will look for another path of cost 4 that does not collide with the first agent. And why do we need to maintain this cost? Because we want to end up with an optimal solution. Okay. So for example, in this case, agent 1 can rerun its planner, and again, it's a single agent planner, it's fast. And find this solution, which is okay, no collisions. And then we solve these 2 agent problems by solving 3 single agent problems. And this is, of course, much more faster. Questions? You're a bit too quiet. Is it clear? Is it not clear? Okay. Okay, so independent detection, simple, not simple, but still this also does not solve all problems in the world. Let's look at this problem. Okay, so in this problem, let's run independence detection. What will happen? Agent 0 will find this path. Agent 1 will find this path, and they are colliding. Does agent 1 have any way to avoid this collision, and with the same cost? No. One of them will have to wait, right? So independence detection is really a 2-agent problem. In this case, it's really a 2-agent problem. We need to solve it. But let's think: what part of the search space do they need to coordinate? All the path? No, right? Only in this place, right? They only need to decide who goes first. After that, all this path, there's no point in searching it in a large 2-agent search space. They only need to decide who goes first. Okay, good. So this I believe was the intuition of Glenn Wagner and Howie Joseph in their M-star algorithm. How does M-star works? M-star looks at the problem, and it searches. It first tries to find the optimal path for every agent. Just look a bit. So it doesn't want to search all this large search space. It says first find optimal path for each agent individually. Then, when you expand the root node, don't generate all its children. Generate only the children that are on the optimal path. So every agent tells you what is the optimal action for it, and you try to do it. In this case, for example, what is the optimal thing for each agent? If it ignores the other agent, what's the optimal move for agent 1? Go to A. Right? And what's the optimal thing for agent 2? 0, also go to A. Okay. So each one of them will tell you to go to A. In this case, this is not possible. So if it's not possible, if there is a conflict, then you backtrack only along this branch, and you explore other options. Okay. If this wasn't very clear, let me show you with an example. Okay, so I'm running this algorithm on this problem. First, find an optimal path for every agent. Done. Okay. So this tells me what is the preferred action for every agent in every location. Then I'm starting the search. It's the same 2 locations search space, but I only generate the node that corresponds to the best action for every agent. So this node. Is this a valid node? No. Is this a valid node? No. There is a conflict, right? Okay, so if this is the case, I backtrack and I start again, but now I do expand all the other options. So now I will expand this. Okay? So this is M-star. Questions? Do you see what we have gained? If not, it makes sense because I haven't shown it yet. So the last line is that then we apply M-star recursively. And what do I mean by this? So now at this stage, for each of these states that are after the conflict, we apply M-star again, which means that we again find the optimal path for each agent, but from this new state. So in this example, what is the optimal path for agent 1 from A? Now it's this path, right? And then going downward from that state, we will only generate nodes according to the optimal path for each agent. Okay, so in this case, take us straight to the goal. So again, what is the high-level idea here? So the high-level idea is that you only open the dimensionality of the other agents. You only consider all of the options of the other agents if you found a conflict. If you reach a state where you have not found a conflict and you pass the conflict, you again try to separate the agents and let each of them walk only on its optimal path. Questions? good. So this is M star, or more accurately recursive M star. And it's nice because it's based on A star, so we can do all kind of heuristic search tricks on that. I'll go get to that maybe later. But still, this does not solve every option, because look at this case. In this case, you start from this location, and if you run M star, what will happen? Each one of them will go through this small bottleneck. So they will, you will run all the way here, get to here very fast, then you will detect conflict, and then along all this branch, you will have to consider all possible options of both agents. So after getting to the conflict, you will have to look at all this large tree. While the location of the conflict is only one location. They only need to agree who will path to the bottleneck first. Okay. So this is the limitation of M star, and we'll solve it in 5 slides with another algorithm. Okay. But I think this covers the main things that has been done in A star based searches. And I will go now to the second line of works, where we search not in exactly this K location search space, but in a different search space. Okay, we'll see what happens. So let's start with ICTS, which is I don't know how to. This is like my firstborn child in this world. So this is the first algorithm I was involved in multi-pathfinding, and it's still the state of the art in several domains. So let me explain how it works. The idea is, I think, simple. You have 2 levels of the algorithm. You have a high level, and the high level needs to guess how many steps each agent will take. The initial guess can be the shortest path for every agent by itself. Okay, so let's say that we have 3 agents, and each agent is 10 steps from its goal, again ignoring all other agents. So the first guess of the high level would be, can I find a solution in which each agent has a path to the goal with 10 time steps? The lower level then, it gets you could look at it as a CSP problem, satisfaction problem. Find me a solution where each agent moves no more than 10 steps. If the low level search algorithm tells no, then the high level needs to guess again. You know what? Maybe 10 and 11. And if it finds, we're done. And this algorithm is complete, and it's optimal, it works wonderfully in several domains. But there are of course some findings to explain. How exactly do the high level guesses the cost, and how do the low level checks if there is a solution of that cost? Okay. And I will say that there is a search algorithm hidden in each of these layers. So let's start with the high level. How do the high level part guesses the cost? So what it does, it spans all possible combinations, more or less. So this is called the cost tree, and the idea is that every node here is a possible assignment of costs to agents. The root of the tree is assigning the shortest path cost to each agent individually. And you go down this tree by adding 1 to one of the agents. So if you look at it, the sum of cost of this solution would be 10, 10, 10, so 30. But the sum of cost of all the solution in the second layer would be 31, because we're adding 1 to each agent. So we're trying, is there a solution of cost 11, 10, 10? So 11 to the first agent, 10, 10 to the other agents. Is there a solution of cost 10 to the second agent? And is there a solution of cost 11 to the third agent? And so on. And again, the idea is you start with the guess, start with the search tree, and we are searching the search tree in the dumbest possible way, breadth first. Okay, so we start with the root, you're trying to find a solution. If the low level tells you no, you're trying to check the next one. No, 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 until you find a goal. Okay. We are doing it breadth first because we want to maintain optimality. If we wouldn't want to maintain optimality, we can search this tree in another way. Okay, now, how does the low level, how does the part that checks if there is a solution, like the part that gives X and bingo, how does that work? Here we are running a depth suspension algorithm, very, very quick, nothing very fancy about it. We do some pruning along the way to remove some irrelevant nodes, but basically it's a depth suspension bound. And surprisingly, it works very well. And I'll explain in a minute why. But in this domain, so what you see here, this is a video game, a map from a video game from Dark Knight Origin. And I have to thank. So you'll see many these kind of figures along the way. So Nathan Sutherland, which is a professor now at the University of Alberta actually. So he made available a bunch of grid maps from this Dragon Age game, and many of you have been using it for as a benchmark for evaluation. And you can see that in this example, we placed agents randomly and we let them run, and the x-axis is the number of agents, y-axis is number of problems solved, so high is good. And you can see that the A star with all the modification, with OD and ID, all the tricks, could not solve more than 35 agents. But the ICTS algorithm could solve more. And the P that you have here, that's ICTS with some additional pruning of the done for the low level. Okay, so this is a nice algorithm. It works well, but let's look how it works. But not always. So here it works very, very well. But what will happen here? So we ran it. So this is the long corridor. The agent needs to swap locations, and they can do that. But one agent needs to go all the way here, and then if you wait a bit, let the other agent go back. And when we ran this with a star, it was amazingly fast, 51 milliseconds. But with ICTS, it took us a long time. Can anyone guess why? Why ICTS crashed miserably in this contrived domain?
Because the guess was really small, so we had to go through a lot of tree.
Yes, exactly. The initial guess, so we had two levels, the high level and the low level, right? So the high level, it needs to guess the cost. And the initial guess here, each agent is one step away from its goal. So the initial step was, you can get there in one, you can get there in one. The actual, I'm just reiterating what, sorry, your name is?
Melissa?
Melissa, so I'm just expanding on what Melissa said, which was perfectly correct. So the cost tree here, it starts with 1, 1, and it needs to go down to actually almost 32, half of 74. So so the high level tree became very large. Okay, and so, but now can anyone guess why it worked very well here in this map? So let me provide some insight. So this is a very large map. So every pixel here is a location. It's about 500 or 500. So it's very sparse. And this means that the optimal solution of all agents is not a lot. It's only slightly more longer than the sum of optimal solutions for the different agents. Okay? So this means that this cost tree was relatively shallow, and that's why this was extremely fast for this case. Okay. So very, very roughly, if the depth of the search tree, this value is delta, then ICTS is exponential in delta. And what this delta means intuitively, it's how far is my initial guess of the cost from the actual cost. So if my initial guess is very good, this would be a wonderful algorithm. If it's very bad, it would be not a good algorithm. Questions?
Is the high-level search is it complicated, or where you start out, the heuristic there, for the high level?
Yeah, so this is a very good question, and I have a disappointing answer. So the high-level search currently is breadth first search, no heuristic, nothing. The only thing we're doing there to save costs is that we solve smaller parts of the problem, like only 2 agents, and see if there is no solution of these 2 agents with some cost, then we rule out some nodes. But we don't have yet any good heuristic. Still, it works well, so there's a lot of room here to do some more research on that. Okay, so now let's go to the last algorithm I think I have time to present. Yes, and we have until 10, right? Okay, good. Okay, so this is the CBS algorithm, the one I like the most. So the idea is we're going back to what we had, the problem we had with M star, where we had one location which was problematic, and resolving who gets to that location first would solve the entire problem. So look at this case, this example. We have 2 mice, but these are not just mice, these are picky mice. So mice number 1 would only want to eat its cheese number 1. Why? I don't know, but it's a picky mice, okay? So if you can see that if they move, there is some bottleneck here. What is the bottleneck? C, good. So if you had A star for that, then A star would expand, look at all the possible combination. For each of them it will C, you can't go to C, you can't get to the same location together, and then only after expanding all of them, it would get to the goal. Okay, so A A star and ICTS, both of them, they still search in this K-agent search space. ICTS in the low level, A star in general. CBS search in the space of how to resolve possible conflicts. How does it work? So we need two basic constructs. The one is conflict. So agent A and B, location and time. This basically means that agent A and B are both planning to be at location X at time T. And we need a constraint, which is agent A don't be at location X at time T. Okay, so given this construct, the idea is that if you have a conflict, you can resolve it by imposing a constraint on one of the agents. So if we have a A and B, they both plan to be at time T at X, we can resolve it by either telling A don't be at X at time T or B don't be at X at time T. These are two options. So the idea is very simple. You plan for each agent individually, then you check if there is a collision. I'm here. If they have a collision, either impose a constraint on agent A to avoid the collision, or impose a constraint on agent B to avoid the collision. And then you continue this process. In every time, you add one constraint to one agent. Eventually, the agent would be constrained enough so that they will find a non-colliding path. The neat part here, that in every step, we only run a single agent pathfinding problem. We never run a K-agent search. We only do a one agent A-star search, only subject to some constraints. Okay, questions? Okay, well, let me say that this algorithm, I think the surprising part is that it's optimal and complete. And I think that the surprising part is the optimality. Because how do we know which one to constrain, A or B? Question? Yes, question? You had a question? Okay, so how do we know which agent to constrain, A or B? And the answer might disappoint you. We try both. So here we span another tree. And the tree here is possible ways to resolve conflicts. A node in this tree is composed of a solution to both agents. So in this case, this is a solution for agent 1. Go to S1, A1, C, and choose 1. And this is 2, S2, B1, C, and G2. This is not a valid solution, of course, right? There is a conflict here. Yeah, but it is a solution. Again, not valid. You can't run it, but it gives a plan for each agent. Okay? So every node in this constraint resolving tree, conflict resolving tree, is a set of path and some other things which I will explain in a minute. And the idea is that you take a node and then you check if it's a goal. How do you check if it's a goal node? Is there a collision? So in this case, there is a collision. Okay? So what do? We try either constraining one agent. So either putting a constraint on agent 1, don't be at location 2, and replanning agent 1, or putting a constraint on agent 2 and replanning for agent 2. I'm saying all, but actually we're trying both. Okay, so one branch constrains one agent, and the other branch constrains another agent. Importantly, every node has a set of paths, right? So it has a corresponding cost. The cost of this path was 6, because 3 moves here, 3 moves here. The cost of this one was 7. So now we search this tree in this manner, expanding a node if we find a conflict branching according to the 2 constraints. And in every iteration, we choose which node to expand according to the one that has the lowest cost. So we run a best first search on this conflict resolving tree. And once we found the goal, meaning once we found a node which has the lowest cost among all other nodes, and it has no conflict in it, we are guaranteed that the plan is optimal. Question?
How will it look for more than 2 agents? We choose every pair of agents?
Yeah, wonderful question. So when we run multiple agents, we can have multiple conflicts. This is what you're aiming? Yes. But it's actually also correct for 2 agents, right? Even 2 agents may have several conflicts. They move to this and this. Yes, so we choose one of them. And it doesn't really matter, or for the sake of optimality and completeness, it doesn't really matter which one. For the sake of efficiency, huge impact, I'll talk about it in a minute, but it doesn't really matter as long as you, at the end, reach a node where you resolve all conflicts, and you search this tree in a best first manner according to the cost. Yes?
To expand on that question, I don't know exactly what you actually meant, but if you have a third mouse that is going to see at exactly the same time as mouse 1 and 2, you you have three mice colliding at the same
Yeah,
point
yeah.
at the same time,
Okay.
so you would have to remove two of them. So
Yeah.
how would you?
Yes. So three-way conflicts, you can always look at them as several two-way conflicts, and you choose one of them and resolve it. Of course, after you resolve it, so for example, if it was the case here, then this would not probably be a goal. You need to go one step deeper. That's okay. As long as eventually you reach a point where you don't have any conflict, you're okay. Okay, good. Okay, so in this example, I won't really go through all the steps, but A star will expand here m squared because it needs to check all possible combinations. But CBS would only run 3 single agent searches, so it would be 3m. Right? So that's significantly less than A star. Okay, so this is the gains over A star, which was cool because A star has all these optimality effectiveness guarantees in it, but here we see it's very nice. But of course, I didn't show you only this algorithm. So I wasted your time in showing you other algorithms because this is not always the best option. So here is a simple example. Okay, so you see here, again, 2 mice, 2 cheeses. And for A star, this is a simple problem because the state space is relatively small. But for CBS, the problem is that each agent here has many options, or 4 options to get to each cheese, right? Agent 1 can go like this, like this, like this, all 4 options. And each of these options conflicts with the other agent's option in a different location. So this means that the constraint resolving tree would have to be at least depth 2. Because it has at least 2 constraints in order to have each agent find its goal. So in this case, it will not work very, very nicely. Specifically, if you want to do some numbers, the CBS expands here 54 states and A star only 8. And it's hard to say which algorithm works best, but I think the general trend that we've seen is that A star works nicely in open space. There is explicit button like CBS works well. But what if I have both? So if I have both, then we have a solution for that also. We run CBS, but we keep track of which agent conflicted. And if we see 2 agents being conflicting too often, so we have if agents conflict too often, then we merge them together to what we call a meta agent, which is a 2-agent agent. The possible actions of the 2-agent action is 5 to the power of 2, so it's harder to solve. But in some cases, it's better. So the idea is you run CBS, agents that conflict too often, you merge them together to one big agent and solve them internally. In this way, we get that agents that are tightly coupled, we solve A star. We solve them with A star. Agents that are not tightly coupled, we only resolve the conflict with CBS. And this creates a nice continuum between the merge when you have a conflict, which is basically ID, independent detection algorithm I've shown you several slides ago, and never merge to agent, which is CBS, and somewhere in the middle is this meta agent CBS algorithm that I just explained. Yeah. I think that now we'll go to some coffee. Because I think, so there's a lot of design choices here. I'll wrap up in a minute just to have a nice closure. So there's a lot of design choices in CBS. When to merge the agent, which conflicts to resolve, is what you mentioned. And there are works on that, but there is still a lot of things to do. Heuristics, how do you search more efficiently this conflict tree and more. But the bottom line is that currently we don't have universal winner coding into our algorithms. They work, and we don't really, so there are some iterations of how to know which algorithm work to apply, but there is still work to do on that. So, this is, I think, what we have time for in the search-based planners. Okay. Good. So let's have a break until 10:30. Any questions? I'll just take offline because I don't want to take your time from coffee. So because we covered like all these options of suboptimal, incomplete, complete, suboptimal, optimal, complete, and but there is one thing that we didn't cover, and I'm not talking about this one because actually there is no algorithm that is optimal and incomplete. Maybe interesting to work on it, maybe not. But what is interesting, I think, is the line between suboptimal and optimal. So all these algorithms, push and swap, when Windows not a proprietary star, these are suboptimal. But I hate the term suboptimal for them because the correct term is I don't know optimal. Okay? It's not suboptimal implies that it's close to optimal, but you really don't know how suboptimal it is. And the solution can be horrible or extremely close to optimal. You have no clue. And optimal, you know it's optimal, but you know the optimal in some cases it's hard. And between totally optimal and I have no clue optimal, there is, I know something about optimal. And I do want to say a little bit about it because I think it's a good place to be, because being optimal, sometimes it's not crucial, but being close to optimal is helpful, and you can get very close to optimal guaranteed and gain a lot of efficiency in there. So very, very quickly, I'd say that in the search literature, there is this notion of bounded optimal algorithm. In other literature, it's called approximation algorithms. The idea is that you have some factor, which is the amount of suboptimality that you're willing to tolerate. In this case, it's called epsilon. And we want an algorithm that outputs a solution that is at most 1 plus epsilon times the optimal solution. Okay? You don't need to know what the optimal solution, but you want this guarantee. Okay? And then epsilon is some user-defined parameter that will tell us high epsilon meaning I'm not close to optimal, but I'll be very fast, and low epsilon meaning I will be optimal, but it's slower. And the question that I'm posing is how to create a balanced optimal multi-agent pathfinding algorithm. And in general, I think there is like two approaches. One is to use different search algorithms, that are designed to be balanced optimal. And the other one is to use heuristics that are inadmissible, that are not exactly accurate, but you know something about them. And I'll start with the bad news, which is some of the algorithms, like ICTS for example, there are no boundless optimal algorithms known for them yet. I'm not saying there can be, but there aren't any. And the reason for that is that although this cost research, I hope you remember it from last hour, so this cost research, so if you remember, how do we search in this cost research? Do you remember from an hour ago? What search algorithm do we use to search this cost research? Breadth first search, right? So you could say, okay, run some other search algorithm that's not breadth first search. Lose optimality, but get some optimality. But the problem is, as we go deeper here, the problem not necessarily becomes easier. On the one hand, it's less constrained, but on the other hand, you're giving more options to the agent. So it's not clear, going down faster in the tree doesn't necessarily means that you're better off. And people have tried that empirically and without any good solution. I'm not saying that there aren't any, but so far, or I'm saying there aren't any now, but someone may invent them in the future. Okay? So this is an open question, and this algorithm is one of the good ones, so it's worthwhile to invest on that. On the other hand, let's be optimistic a little bit, I've shown you a range of A-star based algorithms, OD, ID, M-star, all these algorithms run A-star, and when you run A-star with heuristic, now you can run weighted A-star, or any of the range of bounded optimal search algorithm on that and get efficiency. Okay, and people have done that, this works nice. Okay, if you do not know what is weighted A-star, it's A-star with some weight give on the heuristic. And weighted A-star is just one algorithm. There is a range of bounded optimal search algorithms, some by my group and some by others. So this is one approach. Similarly for M-star, but I think what I want to highlight in M-star, and moreover in CBS, is that in both cases, where you first solve optimally and then run some search on that, there are two places where you can introduce optimality. And let's look at CBS for an example, but it applies also to M-star. So how does CBS work? If you remember, each agent solves independently, and then they look for a conflict, and they resolve it. And we create this big conflict resolving tree, and you search on that. So now you can introduce optimality in both searches. In the low-level search, in the search that gets these plans, you can modify it to run not A-star, but not A-star to find the shortest path, but A-star that tries to minimize conflicts with other agents. And then you get suboptimality from the low level. And you can also search the higher level search, not according to the cost of the solution, but with some added epsilon on that. Okay? In both places, adding this suboptimality to both levels incurs a bounded optimal solution, but also gains efficiency. The interesting, so this is the observation that you can add suboptimality in both levels, also high, also low. And the question, of course, if you are willing to tolerate 10% suboptimality, where do you put the 10%? On the search over the constraint tree or on the low-level search? So there is some work on how to balance that in an efficient way. Here are some examples. I will highlight only one of them. So this is by my group, but I will highlight this one also. So ECBS with highways, the idea is there that you are setting before some predefined, user-defined ways where you prefer the agent to go through. And then you're willing to tolerate some suboptimality if you're going through these pathways. And this helps not only efficiency, but also it outputs a path that are more predictable. You know where the agents are more likely to path, and this is desirable in several applications. Okay. Okay, why it was important for me to steal time from Roman and tell you about this bound suboptimality? Because it's really helpful. And I want to look at this slide. So x-axis is the number of agents, okay, and y is the percentage of cases solved. And you can see that with a CBS, you can solve in this specific map 50 agents. After that, you can't solve any problem. In this specific case, again, different maps behave differently. But what I want you to look at is the ECBS algorithm, which is a bounded optimal search algorithm. And you can see that while CBS solves 50 agents, ECBS can solve 250 agents. And there are two things to note. So first of all, you remember the problem is double exponential in the number of agents. So if you go from 50 agents to 250, I think that's pretty cool. Okay, I'm biased, but I think it's really cool. And the second thing is that the output here is not any solution. It's guaranteed to be at most 1% of the optimal solution. So we were willing to give 1% suboptimality, and we got 5 times more agents. And this is guaranteed. This is not some approximation. Yes?
If we put weighted A star on this graph, where will it be?
Yes. So the A star based algorithms in this domain they did not work well.
Even weighted A star with even weighted A star?
Yes.
Okay.
It's not even to scale. Yes.
Okay.
Yes. Maybe to show it, so this one is I think closest to weighted A star in this context, and you can see that it's not horrible. It's relatively okay, but even this one is not default weighted A star. There is some CBS specific tricks on it. Yes.
All these numbers come from benchmarks. You showed us these maps before.
Yes.
Is there a benchmark also with like start and goal positions of the agents, or I guess this also affects?
Yeah. So this is the pain point. So yes, the benchmark for the maps are common. There aren't several people have said that they will build it, but no one has really put it seriously. So short answer, no. But if someone wants, I can of course send mine, and I'm sure everyone in the community would be happy to share his starting goal locations.
How did you do this? Just randomly sample?
So I think here it was random. I think with some experiment we did random, some experiment we went to make the problem harder. So we picked starting goal location and then choose like the other starting goal location similar to the first agent. So it depends on which. I think this was just random, but okay. That's it. Okay. Yes. One question.
Sorry. Do you have like a difference where you tried with a map where it's more open or less open, and how it compares in those cases? Because I know those dragon age maps.
Yes. So that's a good question. We have it in the paper, and people have. But I will say that the intuition here that as the map is sparser, adding suboptimality helps more, because what suboptimality does is that it pushes the agents to avoid collisions. And if it's easy to do, then adding only a small amount of suboptimality helps.
So in cases where it's
Super dense.
where there's less choices in the map, it helps less.
Yes. Which is not uncommon also in combinatorial search in general. Yes. Okay, good. This is all I think I wanted to waste for Roman. Lots of really cool stuff, but I think that's enough for now. Okay.
Yeah. So we heard a lot about search techniques, and now I'll be talking about a different approach to solve multi-agent pathfinding problem, which is called reduction-based solvers. And basically, the idea of reduction-based solvers is that we are lazy, and we would like to exploit work of others. Okay. So what we want to do is that if we are solving problem P, what we can do is we can translate the problem P to problem Q and ask somebody else to solve the problem Q, because it's not my problem, that's your problem. And then we can use the solution of problem Q for defining the solution of problem P. Okay? So why it's useful? Well, first you exploit all the energy that people put to solving the Q-type problems, and if anybody improves the solver for problem Q, we immediately, for free, have a better solver for problem P, right? So it's like staying on the shoulders of giants. So you just model your problem and somebody else solves the problem. These techniques have different names. It's reduction-based solvers, compilation-based techniques, reformulation-based techniques, or modeling techniques, or whatever, right? The technology that we are going to talk about are just two of them. One is SAT, insatisfiability. Why? Because there was a tremendous increase of speed of SAT solvers in recent years. So it would be good to exploit it if we can model the problem as a SAT problem. Similarly, we can use constraint programming techniques because, again, there are a lot of effort put on defining so-called global constraints, special solvers for special constraints. So if we can exploit them for our problem, it would be an advantage. But there are other formalisms like answer set programming, which is also partly based on SAT, or there are techniques like combinatorial options that can be used there. But I'm not covering these two because there will not be enough time to solve them. So first, let's look at the SAT. I guess everyone probably in this community knows what is it. So when we want to exploit SAT solvers to solve problems, we need to model the problem as a SAT formula, which is a formula in conjunctive normal form. Basically, it means we have Boolean variables, true, false values, and these variables are connected into clauses at this junction of these variables and their negations, which is called the literal. And the formula is a conjunction of all these clauses. And we are looking for a solution, which is instantiation of the Boolean variables to true, false values such that the formula is satisfied. Okay, so this is an example of such a formula, x or y, and not x or not y. By the way, anybody can guess what the formula is saying about x and y? Just by looking at it. So what are the satisfying assignments to x and y? What's the property of them in words?
It's like always true.
Sorry?
I mean, like if x, y, I'm just figuring out. So if 0, 1, like
One is true and one is false?
Exactly.
Different.
Alright? So this is a description that exactly one of x and y's is true, and the other one is false. Right? So we can model many properties like this using Boolean formulas. Okay? So that's the core SAT, but we don't need to model everything in a conjunctive normal form. We can use more abstract expressions, and they could be both logical expressions like, I don't know, implications in addition to conjunction, disjunction, negation, and so on. But we can also use formulas like sum of variables is greater or equal than 1, which is basically the same as a huge disjunction, or we can call it at least one of the variables is true, or we can use the sum of variables is equal 1, which means exactly one of the variables equals 1. Obviously, they need to be decomposed to CNF. So, for example, sum of variables equals 1 is decomposed to at most 1 and at least 1 equals 1, okay? For at least 1, it's very easy. That's the huge disjunction. For at most 1 of them to be true, that's more tricky. There are different translations. A simple one is putting all the pairs with negations, as I showed on the previous slides. But it has a larger formula, so there are more efficient ways how we can translate it. But basically, what I want to say is that we don't need to go to the level of CNF. We can use some high-level formulas that are translated to CNF. We can even use numerical variables, not just Booleans, 0, 1, or true, false. Obviously, again, they need to be translated to Boolean variables. A trivial translation is that each value is assigned a Boolean variable, and we say exactly one of these Boolean variables equals 1, which corresponds to the value, but that's not very efficient. We can model numerical variables using logarithmic number of 0, 1 variables and so on. So So there are ways how to translate them to 0, 1s, and I will use some of them. Okay, so to solve multi-agent pathfinding problem in SAT, there is one major problem. And the problem is that multi-agent pathfinding problem is a planning problem. We don't know in advance how many steps we need to solve the problem, how many actions are there. While solving SAT means give me the formula with a fixed number of variables and fixed number of constraints, and I will solve it. Okay, so first we need to overcome this gap between we don't know the size of the plan, we don't know how many actions are there, and the fixed size of the formula. The trick is used for a long time in planning when it's being encoded to SAT, and it's based on idea of using layered graphs. So rather than finding any plan, we are encoding the problem of finding a plan of a maximum size. Okay? So the layered graph is based on idea that we introduce a given number of layers, I will show in a minute, each layer describing one time step. So we will generate a graph for a given number of time steps for a given make span. We try to solve it using SAT. If we succeed, we have some solution with that make span or smaller one. If we fail, we may need to add one more layer, and we continue until we explore the layers till some maximum, till some upper bound. So to explain the idea, the layer describes positions of agents at a given time. So it needs to encode somehow the graph and also the agents. So this is the initial layer. And then we move to the next layer, which describes the position after performing one action by each of these agents. In this case, we can see they all moved and so on. So these are like 3 layers, so we can encode finding a plan of maximum size or maximum make span 3. Okay? And now the different encodings differ on how we encode each layer and how we encode the transitions between the layers. And that's basically it. Okay? So I will now show you I guess two encodings in SAT to solve this problem. The first one is using the all different constraint, and it's actually using the multi-valued state variables, so numerical variables, not the Boolean variables, but they are translated to Boolean variables. And the idea is that each such variable encodes a position of agent, a node where the agent is at a given layer. Okay, so this is this variable. A is agent, I is the layer, and the value of this variable is a node where the agent A is at time I. Okay, so it's a numerical variable that needs to be translated to Boolean variable using logarithmic encoding is used there. And now we need to define the constraints describing the transitions and the restrictions. So for example, if we want to say that agents moves or waits, then we say, okay, if the agent is at time I at location L, then at the next time the same agent will be either at location L or in one of these locations, okay, it's also L, but a different one, such that it's connected to L. So it moves to the node that is connected. So this is a description of the action, connection between the layers. We would like to say that there are no trains, but which basically means that the agent can move only to a node that is not occupied currently. So what we say is that if at time I plus 1, this agent is in this location, then at time I, no agent B should be there. Okay, so currently the location is free, so I can move there. So it's basically the no train constraint. Okay, just recall that no train constraint also covers no swap constraint, because if you are moving to location where nobody is, nobody can go in the opposite directions. No swap is covered. Okay, and finally, that's why this encoding is called all different encoding. We would like to describe that at any time, no two agents are at the same location. And this is done using the all different constraint, which basically says that all these variables are different. So all the agents at each layer are at different locations. And again, all different is a combinatorial constraint. We need to translate this combinatorial constraint to logical formulas. There are several ways how to do it. again, the simplest one, but the not very efficient one, is saying that each of them are not equal. So we translated binary to and it's a quadratic number of binary inequalities, and they need to be translated also to logical constraints. But there are more efficient ways how we can translate the all different constraints. And that's basically it. Right? So in this way, we can describe the classical voltage and pathfinding problem. Let me now describe, let's say, a more direct encoding, which works surprisingly well, as I will show in a minute. So by direct encoding, I mean that we will be using just Boolean variables. Okay, and the Boolean variable will be like this: what's the agent? It's K. The agent K at layer I is at node J. Then this variable will be true. Okay, so for each agent, we will have a lot of these variables describing positions of the agent at each layer. Right. So the agent K is at node J at layer I. And now we can express the same constraints as before. So we would like the agent to be at exactly in one node in each layer. So this is the constraint that I already showed you before. So exactly means that it's not possible for the agent K at layer I to be at two different nodes J and L. So it's not possible that these two variables are true at the same time. And similarly, we would like to express that it's at least at some node. So it's simply this junction of all these variables through the J. So we say that agent K at layer I is at some node J. So it means that exactly one of these variables for that agent and a given layer will be equal to 1. Okay? If we want to say that two agents are not placed at the same node at the same time, we use a very similar constraint to this one, but now we have two different agents, K and H, at the same layer, and we say that they cannot be placed at the same node J at the same time. Okay? About the actions of the agent, which are the transition constraints between the nodes. So we want to say that if the agent is at node J at time I, then in the next layer, I plus 1, it might be at the same node, so it's the wait action, or it will be at some node L, which is connected to J. So this is describing the wait action, and this is describing the move action. Okay? And we also need to show it differently. If the agent is at some node, it must arrive there. So we say that if at layer I plus 1, the agent will be at node J, then it was at that node J before, or it was at some node L such that it can move between J and L. Okay? So we describe the constraint from both directions. The reason is that we don't want to split the agent or something like this, or merge the agent. Okay? And finally, about the no swap and no train constraints, again, it can be expressed directly. So if I have agent K, which moves from J to L, then what is this? It's not possible that there is some agent at position L at the layer I, and there is no agent at position J at the layer I plus 1. Okay, so it means that if I go from I to J, then J was free the step before, so it was empty, and I will be free the next step, right? So it's like I move the agent, so one of these nodes will remain empty always. Okay? So this is a direct encoding. You can see it's really direct, so it's a conjunctive normal form, Boolean variables only. Okay? If we look at efficiency of these encodings, again, this is a graph, grid 8 times 8, 10 obstacles, I guess, random placement of agents. So we already saw the algorithm ODID, which is the search-based algorithm. This is the number of agents, and this is the runtime to solve the problems optimally. So we can see that the direct encoding is actually surprisingly good. At the beginning, the all different encoding is very good, but then as the number of agents is increasing, the all different is no more working, and the direct encoding is still working. There's also another encoding called inverse that is even older, and it's more complex, using some numerical variables as well. I did not describe, okay? So these are the sub-encodings. Any questions about them? So it's just about the idea of how I can describe everything using 0 ones. Okay? That's it.
I just what didn't I mean I did get how you describe the states. I mean like by these 0 ones, but how do you like describe kind of like transitions via this layered graph? But how do you like expand nodes, or I mean like what is actually the final formula you're going to satisfy?
Okay, so it's a conjunction of all these. So for each layer, you generate some formulas, and you generate formulas connecting the layers, and in conjunction of all of them is the huge formula that you saw. So first, and I will cover it in a minute, you define the make span, the number of layers, and then for a given number of layers, you define all these formulas. Obviously, I did not say that you also need to define the initial locations, which are the values at the beginning and the values at the end, right? So you know them.
Yeah, but how do you define the values in the middle? I mean, like, so.
Oh, you don't define them. The solver finds them. So you just define what are the constraints which connect these variables. The subsolver finds a solution, which means it finds assignment of values to the variables. And obviously, from this, you need to decode the solution, right? So it will instantiate all these variables, and then you just follow them and you say, okay, this is the move action, this is the wait action, and so on, right? So it's the solver who decides about these values in the middle.
I wonder, okay, do you have kind of just like a naive example of how it exactly looks like on like some simple instance? Yeah, I mean, like that's the idea.
Right?
Yeah,
So you have like a variable which says this agent is in this node, and the variables that this agent is in this node, and that node will be 0. Right? So you encode one layer using a set of Boolean variables, and instantiation of them exactly describes the situation. The agent is here and the agent is there. Then you have the variables for this layer, for this layer, for this layer, and because of the constraints, you know that it really corresponds to allowed move or wait.
Okay, I was just trying to.
I mean, I don't have the
I was just trying to figure, to comprehend, I mean, like how actually, like this situation looks in this formula notation. I mean, like, so how many formulas you have when I see these 2 agents and like a 10.
Oh, okay. Oh, yeah. So yeah, we can
100,
define precisely the number of formulas because you can look at the indexes. So I did not say these formulas for each I and so on. So yeah, it's quite easy to tell what's the size of the formula for a given problem. It's large. Yeah.
Like for this problem, like is it like 100 formulas or like?
I don't know the number, but
1,000. I don't know.
Well, no, it's well, the number of clauses maybe thousands. It could be even millions, but it's not a problem for the subsolvers because of the structure.
So it could be 1,000 and even like.
Okay, let's look at this. This is the direct encoding. Okay, so we can see it immediately. So, for example, this is for each agent K and for each layer I. So multiply the number of agents by number of layers, and this is the number of times this is repeated. The same for this one. Okay, this is for each pair of agents K and H. Right, so it's like quadratic and so on. So from these formulas, you can easily calculate in advance what's the size of the total formula. Yeah.
I just want to make sure I understand, because if you go back to the example, the simple example with the graph, it was it's quite simple because in this case, like there's basically only one possible movement for the blue one to make. It can only move to B2. So the next layer is.
Oh no, it can also wait.
It can also wait. Okay.
Yeah.
But then, so my question is, do you get the first layer that you get here, number one, that one, how did you know that that first layer would be that it would move? Like, wouldn't you get at each iteration of a layer, wouldn't you get as many layers as you would get nodes in a simple A star? Like here you can have two.
Not
blue
really, because in A star, each node corresponds to situation. Let's say allocation of agents.
Yeah.
In this, you just have a formula and possible instantiation of values. What's happening here? Possible instantiations of values define the number of nodes in the A star.
So it's just an
So
example.
the size of the formula.
So this slice, which has number 1, is just an example. So it's not.
This is actually a solution, right?
Yeah.
But each slice is a formula with 0, 1 variables.
With all possible options.
And if we instantiate them, this is one possible instantiation, right? So this is not what the formula is describing. This is actually instantiation of the formula or instantiation of variables.
So you,
But
would
the
have, so you would have another layer, which would be that the blue weights.
No, it's not a different layer. It's the same layer with the same formula, but it has variables.
Okay.
Okay, but if you instantiate the variables, you get the particular situation. But the formula is fixed size. I mean, it describes all possible situations, but the size of the formula does not depend on the number of possible situations. But basically, instantiation of variables describes all possible situations. So the size of the formula is fixed. So it's not related to the size of state in A star, but the number of evaluations, instantiations, all corresponds to A star. Maybe.
Yeah. So you only instantiate the first layer and the last layer. And all the middle are just constraints over the variables.
Yes. Yeah. Only the first layer and the last layer are known, and in between there are just variables. And after instantiating these variables, we know the situations there. But the beginning is just a formula.
Can you say that in between it's random? Can you say that in between it's random?
No, it's not random because it's connected through the constraints. So these constraints are defining what is allowed and what is not allowed. Okay.
One more out-of-box question. Is there any communication with the agents? Like
You mean if the agents communicate?
Yeah.
No.
Okay.
Well, I mean they don't communicate during execution, but obviously they communicate through the locations because it's a centralized approach, right? So each agent knows about the other agents because of the formulas. Okay. So he can. Okay, let's go there. We can call this a communication because it connects variables of different agents, right? So if one agent moves from J to L, it says that no other agent should move from L to should not be at L, for example, right? So it's not communication at the level of communication between agents, but because it's a centralized approach, the agents know about each other. So did I clarify it?
Yeah.
I mean, the trick is that you just encode.
I
Constraints, it
It's
must
a
be
bit
true.
hard to comprehend until, I mean, like it would be easier if you have an example. I mean, like how exactly the formula looks like. But now,
Oh,
for
it
this
would be,
piece of question,
even for a small problem,
I
it would be large formula.
I understand that it would be large just just to see it with.
So that's why we use like the abstract description of the formula, and then you need to put for each k and for each j and so on. So the formula is a connection of all these abstract formulas. Any other questions?
Are there works which use extensions of SAT like SMT?
I'm not aware that anybody is using SMT because right now for the numerical relations, because they are not really numerical, they are translated to SAT. I think we tried SMT, but it was not working. but it's about encoding. This problem uses the numerical variables not because of numbers, but to simplify the encoding. So there might be a reason to use SMT when we go more to numerical domains. But I will use constraint programming for this.
I'm not sure if you will cover it, but is there any way to make this suboptimal?
No, it's optimal in terms of make span, but I will be covering objectives later. So I just described the model for a given number of layers, and I will cover the objectives later. But it's for solving optimal solutions.
Yeah.
So in both make span, for some of course we need something slightly different, but still the encoding will be the same. So it's for optimal solvers.
Yeah, but the R works on how to take that and make it optimal.
Okay.
Yes. There are some very recent forms.
Yeah.
One question on that result. I'm not really familiar with SAT solvers, how they work internally, but can you give an intuition on why the SAT solver makes it so much easier to solve this compared to planning?
So how SAT solvers are working? Yeah, this is where the surge is.
It's like deep learning.
So SAT solvers use a combination of propagation and surge. So they use something which is called unit propagation. If you have a formula, you can deduce what's the value of some variables because it's inevitable, it's not possible. Then if you cannot deduce anything more, you branch. So you select some variable and you try true value and false value. So this is where the search is. But why they are so efficient is because they can also learn some structure. So if they find a dead end in the search, they can find they can find a reason why it's a dead end, why the formula, why the instantiation is not correct. So they can include some extra clauses. So the next time they can avoid these dead ends, especially if it's a structured problem, not a random formula, but a structured formula like this one. They are very efficient. And by very efficient, I mean millions of variables and clauses is not a problem for them, for structure. Right? So even if these formulas are really big, it's still, for SAT solvers, it's very, very fast. So that's basically a crash course to SAT solving, but it's a huge error. Any comment? Okay. So there is one more model that somehow shows how this is working. It's very similar to the direct model. We use the Boolean variables there, but we use non-logical constraints. We use these constraints that I showed before. So the idea of the variable is the same as before. 0, 1 variable describing the position of agent at a given time, if it's in the node or vertex or not. And then we can describe the constraints in a slightly different way, like agent occupies exactly one vertex, so we take all the variables for that agent in a given layer, we make a sum of them, it must be equal 1, which is exactly one constraint that has been described using these two clauses before. We can say that no two agents occupy the same node, so we take all the variables for that node in a given layer through all the agents, and the sum of them must be small or equal to 1, meaning 0 or 1 agent can be there. This is like the at most 1 constraint. How to describe that the agent moves. If the agent is at vertex v at time t, then in the next time it will be in one of the neighbors where we include the node v in the neighbors. So you may ask, oh, why is greater or equal than 1? It should be equal to 1, right? So the agent moves there. It's just a small trick because in SAT solving there are many small tricks that make it efficient. This constraint together with that constraint actually gives equality, but the reason, anybody guess why we are using greater or equal than 1 here rather than equal 1?
Maybe it's easier to transform into some logic.
Exactly, right? Greater or equal 1 is at least 1, which is a simple disjunction. While if we use equality, it's a simple disjunction plus at most 1, which is quite complex, right? So by these tricks, we can make solving practically more efficient. Right? And there is one more trick, some simple preprocessing. And this preprocessing is based on idea that not only the first layer and the last layer are fixed, but we can also fix some variables in the layers between. So for example, if I am in the second layer, all the nodes that the agent cannot reach in one step cannot be used there. So I can set these Boolean variables to 0 because the agent cannot be at time 1 at this node. Right? So somehow I can send the agent to all possible nodes, and the nodes that are not reachable in a given layer are set to 0. It's not possible to do so. And it significantly improves, again, efficiency. So these small tricks are what's important there. So even if the models looks quite simple, a lot of these tricks are really necessary to make them efficient. So just to show the comparison, yeah. So this is the reason why I showed you this model is that the original models were quite hard to encode. I mean, you need to do all the translation to SAT. In this model, we use a system called PyCat, which is Prolog-like language, and this system includes automated translation of constraints to SAT, CP, mixed integer programming. So you can really express the constraints at high level, exactly as I showed in the previous slide. So you can really write the constraint like this. Okay, so this is really a model, executable model. You can run the solver there. If I go, okay, we can skip this. So this is setting the position of agents in the first layer and in the last layer. So you can see we set the variables to 1, and through the other constraints it's propagated that the other variables are set to 0. This is the sum constraint. The agent occupies one vertex at any time. So you can see we rewrite the sum equals 1. This is the non-conflict. The sum is small or equals than 1. So we just say, okay, let's make a sum of these variables where we change the agents and the node and the time is fixed. And this is the description of transitions, right? So we take the neighborhood and we say, okay, the agent is at node V, then it must be in one of the neighbors U in the next time. And then you just ask solve, and the system solves the problem, okay? The nice thing is that if you want to solve the same model using CP or mixed integer programming, you just say at the beginning, use SAT, use CP, use mixed integer programming, and the system automatically translates these constraints to appropriate constraints for each model.
I'm sorry, here AS is agent numbers, right?
A is agent, I is layer, and V is node.
So, I mean, like, I'm just trying to go from top to bottom. So K equal lam AS.
Oh, K is the number of agents. So we have K agents.
Okay.
Okay. We have M plus 1 layers, and we have N nodes. Okay. So this is really a complete formula written in program, right? So for each, generate this number of constraints and so on. So it's a complete example of the formula.
How do we?
Is the list.
Yeah. How do we get the initial and destination locations? I mean, like.
Oh yeah, it's described using facts somewhere. In particular, we have an array which is in the input, and this array describes for each agent a pair of nodes, V, initial node, and the final node.
Oh,
So in the input, we get the locations.
So so the locations are in this array.
Yeah,
right?
yeah.
Okay.
And the graph is stored in the memory, so we extract the graph using the neighbors. So there is a function that if you give it a node, it will return you all neighbors of that node.
And M is also kind of input parameter here, like the number
And
of layers.
N is the number of nodes in the graph. So at least you need to, the nodes are numbered 1 to N. So you need to know the number.
I'm sorry, M.
M. M is the number of layers, and it's generated here, and I'll be talking about it in a minute. So it's the make span. So the idea is that you calculate the lower bound and upper bound for the make span, and you simply assign M to lower bound, and you try to find a solution with the given make span. If it fails, this is a prolog, so it backtracks and it generates one more layer. it repeats it until it finds a solution or it reaches the upper bound. Right? So we have this formula of lower upper bounds that calculates the lower and upper bounds for the make span, and then we start with the lower bound and we add layers until we reach the upper bound. So either we find a solution or we fail. So yeah, this is really executable code. I mean, you can download it and you can run it and you can modify the constraints easily. You can even add constraints like the k-robustness that I described before. So it's very, very easy. You just say, okay, if I want to be in this node, then that node should be free in the previous k layers. That's basically it. Okay, so this is the k-robustness. Okay, so this is a comparison of this code with the other codes, runtimes on some problems. So you can see if we are solving, if we are looking for make-span optimal solutions, this is a pure SAT solver, okay? So this is the direct model that I described it before. So we are somehow comparable in runtimes, but it's much easier to maintain this code. This is an ASP solver, answer set programming. I did not cover it here, which is another declarative approach to describe the problems. For sum of costs, we can use the same model, but there need to be some tricks. I will describe them in a minute, how we can optimize the sum of costs. Because as you may guess, SAT is very good for minimizing make span, because we find the first solution with the smallest make span. But this is not enough for sum of costs. Okay? Okay, so yeah, question about.
We talked about CBS before. So why is CBS not in the left column with the make span?
Why it was not there?
I can answer that. So CBS was at least the first series of papers were on sum of cost, not on make span.
Okay. But in theory, it's not a problem.
Yes, it's not a problem. Yeah, but I'm not sure we have a code for that. So we have a code for that. We did actually, but that came I think after.
Yeah. And to answer a similar question, why ASP is not here? Because ASP was not able to solve the sum of costs, so it's not there. So we use one of these for each column.
And the figures in the cells are seconds, right? Runtime.
Yeah, this is a runtime in seconds, and this somehow indicates the size of the grid, the number of agents, and this is probably the percent of obstacles. I don't remember exactly the details. So it's one of the benchmarks.
So, if I get it right, that means that for sum of costs, CBS is faster and not much worse.
This is for optimal solutions, so CBS is very fast. There are some problems that cannot be solved by CBS. So we have a new version for this one, for the PyCat, for sum of costs that can solve all the problems. So it's better than CBS in those problems that CBS cannot solve, but if both of them can solve it, then CBS is much faster. Right? So we have a new trick in the PyCat model that solves all 20 problems in 10 minutes, but it's much slower than these two approaches. Okay, so about the objectives. So I did not say how we do the optimization. Okay, so for make span it's easy. For make span, we can estimate the lower bound and upper bound for the make span, and then we iterate between them. So we start with the lower bound, we generate the SAT formula. If we find a solution, we are done. It's make span optimal solution. If not, we add one more layer, we call the SAT solver. Is there a solution? Yes, we are done. Not, increase the layer. So make span optimization is quite straightforward in this model. For sum of costs, it's more tricky. Okay. So one easy thing is that we can first find the best make span, and then we can optimize the sum of cost. But it obviously does not mean that we get the best sum of cost. It's like lexicographic ordering. Make span and then sum of cost. Okay? If we want to really optimize the sum of cost, we can do the following thing. Rather than generating a smallest number of layers, we actually use the upper bound. So we generate much more layers. So we allow the agents to move longer, and then we optimize the sum of cost. Okay? So optimize means basically running branch and bound in terms of sub, which is possible. It means repeated calls to sub. But it's very naive. Why? Well, we get a huge formula. So if we have larger problems, the upper bound for the make span will be so big that the formula will be really, really huge. So just generating the formula makes, gigabytes. So it's not really tricky. But there is a trick proposed a couple of years ago that we don't need to do it this way, but we can do it incrementally. And the idea is that we calculate the lower bound for sum of cost. Lower bound for sum of cost is quite straightforward. Calculate the shortest path for each agent and make a sum of them. This is the best solution you may get. Okay? So we calculate this lower bound, and then we try to find the first number of layers when we can find some solution. And we verify if this solution has the cost of the lower bound of sum of cost. If not, then we increase this lower bound and we add one more layer. So we are somehow incrementally adding layers and increasing the bound for sum of cost. And the first layer, when we find a solution which corresponds to the current bound for the sum of cost, is the optimum. Okay? And actually, the trick that we did not publish yet, so don't tell anybody, in the PyCat is slightly different. First, we try to find the first make span where some solution exists, and we optimize the sum of cost for this make span. So this provides us upper bound for sum of cost. And we make a difference of the upper bound for sum of cost and the lower bound, and we add all these layers which are equal to this difference. So rather than adding one layer, we add all of these layers to the system, and we solve it again, and we optimize the sum of cost. So actually, it looks like two calls. First is optimization of sum of cost for a given smallest make span, and then for the other make span. It's actually many calls because it's branch and bound. And using this trick, we can solve much more calls. So sum of cost is a bit tricky for these compilation-based approaches, as you can see. The precise description of how this increment is done is in this paper. Okay, so that's about the sub approach. Any questions? So I now move to the CP approach, which is actually very similar, but it's somehow more flexible. So in CP, it means constraint programming. We encode the problem as a CSP, constraint satisfaction problem. Who is familiar with CSP? Surprising, because I believe this is one of the basic topics of AI, like SAT is one of the basics of AI. So CSP is very similar to SAT. We have variables, but now the variables have finite discrete domains. Not just 0, 1, but numbers, whatever you want. And then we have constraints. And again, the constraints are arbitrary relations between the variables, not necessarily logical formulas. You can say A is smaller than B, A plus B equals 3. A is different from B and whatever. Okay? So they are basically relations. And solution to a CSP is instantiation of values to the variables satisfying all these constraints. Okay? And what's crucial for applying CP is how you model the program, how you select the constraints. And it's important because there are many so-called global constraints with specific solving techniques behind them. So let me show an example. We have these variables, and this is a description of domain. So we have these variables with domain 0 to 9, these variables with domain 1 to 9, and these are Boolean variables. And these are the possible constraints. Anybody guess what problem is it? The famous problem? And I hope the letters will help. Anybody guesses from the letters and constraints what problem is it? It's a classical combinatorial puzzle.
Sudoku?
No. In Sudoku we need all different constraints, so these are numerical constraints here. So there is one all different, but
It's like a sum of the words. course.
Yes, you know, right? One of these examples, send more money. So it's called, how is it called, algebrogram. So the task is you have the letters and you need to assign a digit 0 to 9 to letters such that different letters are assigned to different digits, and the first letters S and M are not 0. That's the only restriction, and all the letters should be different. So what you do in CSP is just formulate a problem like this, define the variables, define the constraints, and then you ask the solver, like the SAT solver, to find a solution for you, to instantiate the variables. Okay? In this case, the solution is this one, and I think it's a unique one. The other solution is okay. So as I said, staying on the shoulders of giants. So somebody program a solver, you just formulate a problem, send it to the solver, and the solver produces a solution. So we can encode multi-agent pathfinding in this way. So you may ask, what's the difference between CP and SAT? So obviously, every SAT model is a CP model. We have just Boolean variables, and specific constraints described as clauses. So there is a very close relation between them. The small difference, maybe big difference, is that in CP you can directly use numerical variables, so you don't need to translate them to Boolean ones like in SAT. And the same is constraints, so you can use numerical constraints like A is smaller than B with very efficient filtering, which is not that easy for CP, even if for SAT, even if it's possible. And about the solvers, it's again very similar, the CP solvers and the SAT solvers. So in CP, the solver is interleaving, maintaining local consistency and search. So what does it mean? Local consistency means that if somebody gives you a constraint, you can remove values from domains of variables that are violating the constraint. So if you have a constraint A is smaller than B, then every value in A that does not have a support in B can be removed from the domain. Okay? To give you an idea, if I have an all different constraint that says that all values are different, and I have 3 variables, one variable is domain 1, 2, one variable is domain 1, 2, one variable is domain 1, 2, 3, to make it locally consistent, it's clear that values 1 and 2 cannot be used for the search variable, so I can remove them from the domain, and I don't need to try them during search. Is it clear? Right, so it's like a coloring problem. So I have 3 nodes, 2 colors for one of them, 3 for the other one. 1 and 2 cannot be used there because it's used for the first 2. And this filtering is done by ad hoc procedures that are assigned for these constraints. So for example, all different is based on finding matching in bipartite graphs. So it's like the unit propagation in SAT, and the rest is again search. So if there is still variable that has small values, you select some value, you assign it, you propagate the information, and you continue. Okay? So as I said, these global constraints are very important there because they somehow provide the power of specialized solvers to CP. Right? So you may have a solver to solve all different constraints, so we can encode it there. This is especially important for scheduling problems. So for scheduling problems, many constraints has been defined, and we will use them to model multi-agent pathfinding problems. Okay, so about the CP models, to make it obviously every SAT model is a CP model, so every SAT model that I presented before can be solved using CP. It's not very efficient. So for CP models, we use a slightly different approach where we somehow separate what we call planning and scheduling. So planning means finding a path for the agent. Okay? Which nodes will be visited, and this can be modeled using several ways like flows and so on. I will show it in a minute. And scheduling deals with the collisions. The idea is that when agent visits a node, we assign 2 times. The time when the agent enters the node and the time when the agent leaves the node. And these 2 times define an activity of being in that node. And if we have these activities for each agent visiting the same node, we may ensure that they are not overlapping in time. which means the agents are not visiting the node at the same time. And we can use the powerful techniques from scheduling to solve these problems. Okay? So basically, the scheduling part ensures that there are no capacity conflicts. And obviously, we can introduce them for arcs as well, and so on. Okay? So if we do it this way, it's somehow more general than the classical approaches to multi-agent pathfinding because, for example, we can include durations of actions. In classical multi-agent, it's like action is moved there, one time unit, wait, okay? Now we can include distances. So it takes some time to move between the nodes, okay? Or we can include capacities. So we may have nodes where several agents can be at the same time. So we can just introduce a larger capacity. Or we may introduce the capacity of edges. So we may allow more agents to use the same edge arc at the same time, okay? Like a street, so there might be more nodes there. And it will be very simple, we just increase the number from 1 to something larger. Question?
No.
Okay. So that's the idea and the reason to use CP. So it's more flexible in terms of describing the problem, okay?
I actually have one question. Can we describe non-integer durations in this case?
No, CP is based on discrete variables, so we always use integers, but if you want to describe non-integer, you just increase resolution. That's possible, right? So if you want to say it's half a second, then half is not possible, so you will measure half seconds as time unit.
And it won't, will it increase the difficulty to find the solution if I increase the resolution on this timing?
There is no clean answer to this. So obviously, it looks like the search space is larger because now you have more values for the variable if you use a larger resolution, but the propagation techniques are frequently, especially the scheduling ones, are working with intervals.
Yeah, that's
so therefore, it may not be that big problem if you use scheduling models. But in general, yes, there are more options. But many models are not really assigning values to variables, but they are posting like precedence constraints and so on. So it will be some influence, but probably not that dramatic as one may expect. And you will see that it's different from SAT, where you translate the numbers to Boolean variables, because then obviously the size of the domain influences the size of the translation.
But not here.
In CP, it's not that strong. Okay, so I will show you two models. One is a model that somehow simplifies the planning stage and simplifies it by assuming that no agent returns back to any node. So revisits are not allowed. You will see the reason. The reason is that for each node we can define just one activity describing when the agent visits this node. And this activity may be empty if the agent does not visit it. So we don't need more activities for each node. And I will show you some basic models based on network flows, finding paths, and scheduling problems. The advantage is that we don't need this layered model like in SAT. Right? Because if the agent cannot revisit the nodes, we know the number of layers. Okay? And we don't use the time slices because we use the time to enter and time to leave. So we have like for n nodes, there are at most n activities for each agent. Okay? But obviously, if you want to solve the classical multi-agent pathfinding, we need to allow revisits. Okay? And I will show you the model how to do it, which will be also a layered model, but the layers will be different here. Okay? The layers will be based on the number of revisits rather than number of time steps, which has a different time complexity because in SAT you need the number of layers corresponding to time. So the longer the make span is, the more layers we have. In this case, the make span is not important, it's the number of revisits. Okay? So let's start with the first model. We call it a flow model because it's based on network flows. And the idea is that for each agent, we use a variable describing whether that agent visits a given node. It's called use. And the flow, use is for arc flow. Flow variable describes whether the agent is using a given node P, 0, 1 variable, and use describes whether the agent is using a given arc or not. And the flow model is basically saying that if the agent is using some node P, then it must enter that node. Okay? So it must use one of the arcs going there. And because these are 0, 1 variables, this constraint is basically saying that it will use exactly one arc to enter it. Okay? And this constraint is for leaving. So it's a classical, what's it called, flow consumption constraint, which says, okay, if you enter the node, you need to leave it, and because it's 0, 1, you can enter the node once and you leave it once. Obviously, you never enter the origin and you never leave the destination. Okay? So when you reach the destination, you are there. Okay? So this is the planning model. So if we satisfy these constraints, we basically find a path from origin to the destination, because origin and destinations are the only nodes that are has flow set to 1 in the beginning. Okay? And then, how do we do the scheduling? Well, for each node, we introduce 2 numerical variables. We call them in and out t, and the meaning is obvious. In t means time when you input, enter the node. Out t means when you leave the node. Okay? And now the constraint is saying that if an agent is using node P1 and using node P2, then it cannot be there at the same time. So either it's first in node P1 before being in P2, or vice versa. It's a classical disjunctive constraint that says that those 2 activities are not overlapping. So 2 visits of the node cannot overlap. Obviously, this is not enough. We also need to specify that if you move somewhere, it takes some time. So we need to specify the temporal constraints that basically say, okay, if I use some arc, then I leave the node at the beginning of the arc, then it takes me some time to go there, and then I enter the node after that. Okay? So I specify the constraint that connects the time for leaving one node and time for entering the node. Okay? And obviously, the time when you enter the node must be before the time when you leave the node. Okay? So this is the capacity constraint, so we cannot overlap. And this is the temporal constraint. So if we follow the path, then the times are assigned correctly. Okay? And that's it. Put it to the solver, find the solution. Okay?
And all these constraints will be translated to a CSP?
They are already. This is already CSP, because in CSP, the constraint can be any relation. So you can express the constraint exactly like this. So no translation is necessary. It's one-to-one. Okay. So this was a flow model. So flow model uses like network flow ideas. We also defined a model based on paths. So the idea of paths is that each node must have a predecessor and successor in the path. So we use 2 variables, prev and next, previous and next one. And the connection is that if the previous node for x is y, then the next node for y is x. So basically, it connects these variables. And P is the agent, right? So for each agent, we defined a separate path, like before. So obviously, it will again generate a correct path. And for the nodes that are not visited, we use self-loop. Right? So the previous node is the same node. So we cover the rest of the nodes by self-loop. And then the rest is the path. About the scheduling, again,
Sorry.
Question?
Just a pretty stupid question probably, but the first node doesn't have a predecessor, right?
Yes, we can connect it to the last node. That's the trick. Thank you.
Okay.
So exactly, we can set the value of predecessor for the first node to be the last node, and the successor of the last node to be. So we set these values, so we actually form loops. So a good question. About the scheduling, we introduce activities. So now it's the time where we are moving to scheduling model. So for each node, we introduce an activity. Activity has a start time and end time. We had it explicitly in the previous model. Now we have the activity that covers this. And what we say is that activities for all agents are not overlapping in a given node. So this is this is actually a global constraint describing what I described here using the disjunction. Okay, so this is a global constraint. So we can exploit some specific scheduling techniques for this. No overlap means rectangles are not overlapping in time. Okay, and about the temporal constraints, again, we need to connect the activities according to paths. So basically, we want to say that the end time of the previous activity plus the duration to move to the next node equals the start time of the next activity. So we use the variables as index to connect leaving one node and entering the other node, like we did before. Okay. So this is the path model, and the last model is pure scheduling model, and it uses activities both for arcs and for nodes. Okay? And the idea is that for each node, we introduce one activity describing when the agent is staying in this node. If it's not staying there, then the duration of this activity is 0, it's empty. We introduce two activities describing that the agent must leave the node if it's not the destination, and must enter the node. Okay? They are connected in the way that if this activity is used, then both of these activities are used. So it's these activities are so-called optional in terms of scheduling. Optionality means we decide during scheduling if activity is included or it's not. Okay? So this is the constraint that describes this relation. If the node activity is present, then the enter and leaving activities must be present as well. And for each arc, we also describe specific activities if the agent is using them. Okay? And then these activities are also connected. So for example, if I'm entering the node, I know that this activity must be used. If this activity is used, then I must enter the node. That's the idea. So they are somehow connected. Okay? So these are alternative ways how we can enter the node. Okay? And the scheduling part is very simple. We just say, okay, the activities are not overlapping in nodes and in arcs. And the temporal constraints are also quite simple. We just say that these activities, if we connect them, the end time of the int activity equals the start time of being there. The end time of being there equals the start time of leaving the node. And thanks to the scheduling, everything is synchronized. So when we decide which activities are present and when they are present, we get exactly the schedule plan for each agent. Okay? So if we compare the models, again, I'm not in the paper, we have details about the data. So this is like a global view of these three models. This is like a complexity or the size of the problem. So we solve a lot of problems. So we can see that the model with optional activities is somehow more stable, even if it's not the best one. So for small problems, the flow model is better, and then suddenly the flow model becomes worse for some reason, and the scheduling model is somehow more stable. To give you somehow the idea.
What is the vertical axis?
This is runtime.
Runtime.
Right. This is a runtime. I believe it's in milliseconds or something like this. Okay. So now lower graph is better. And obviously, the lower and more to the right is better. This is like a global for all the problems together that we generated. But to understand the behavior, we try different map sizes. Okay, this is like 5 to 5 and 8 to 8, and we can see that for smaller maps. The flow model is actually quite good, but the larger the maps we have, the flow model is becoming worse and worse. So it somehow indicates when a given model is better. And if we try to look at the number of agents, we can see perhaps even a stronger correlation. So again, for a small number of agents, the flow model is better, but the more agents we have, the better the scheduling, the model's optional activities is. So this is just like brief analysis of the behavior of different models.
And the horizontal line means that
these are always the problems with increased complexity.
No, I mean like this.
This is runtime. This is runtime.
Yes. So the thing is that you have not. You just stop the experiment when the runtime exceeds the 10,000.
10,000. Yes.
That's why.
Yeah, that was the end. So this is indicated here, right? So that was like a timeout. But still, I mean, it says that in this case we will go even more up with the pass model, and the same is here. So it simply takes too much time.
So path is always the worst model, right? Because
it's never the best one, I would say. Okay, it's well. There is still some surprising behavior. So you can see at some regions, the pass is actually a good one. So there's one. There are regions where the pass model is not. It's the best one, right? We still don't understand fully what's happening.
But I mean, like it is always kind of almost always the first model to reach the
level. Yeah.
The upper limit.
The problem is probably the size of the models.
So, and do I understand right? It's like for 9 agents, 10. What figures on the vertical axis really mean? I mean, like 10,000, or it's like 10,000.
It's
like
100,000.
10
It's
10.
100,000 seconds, which is 100 seconds.
So it's 100 seconds,
100
right?
seconds.
So for 9 agents.
Yeah.
Looks like.
Not big problem, I would say.
Yeah, I mean, like, so it's not a big problem, 9 agents, but still the solver cannot solve it, right? Within 100 seconds, which is like a little bit less than 2 minutes runtime.
We are talking about optimal time, right? So it's in this case, it's a make-span optimism.
I think it is important to know that Roman didn't say the size of the grid. Like 9 agents is very easy if you're in Dragon Age map, but if you're in a 10, like 4x4, it's almost tile puzzle. Right? So it depends on the grid. I don't know what the grid size here, but I'm assuming it's very small.
The grid size were like this, right? So 5 to 5 to 8 to 8. Right? So the number of the size of the map is not big. So actually, if we increase the number of agents, it's being too crowded. So the problem is actually not that easy to solve. In this case, we did not use a complete random setting. I don't have the slide here, but actually we intentionally try bottlenecks. So we have a map where there was a bottleneck and the agents need to use that bottleneck. So it's actually not easy problem because there are many agents and not that much space there. So that's why it takes so much time. So it's like an academic benchmark to be made hard.
What were the numbers on the x-axis? You probably said it. But
You mean these numbers?
on the x-axis.
This is just a number, the identification of the problem, and they are somehow ordered by
Complexity.
Complexity, but the complexity is defined by the runtime
Okay.
somehow. So it's like more 1,600 problems. So that's why we use just 100 seconds the limit, because it's a huge number of problems. So yeah, it's just an idea of the problem with increased complexity. I believe so. Let me show it precisely. This is not the idea of the problem. This is the number of problems we can solve optimally until a given time. I believe this is the order. So it's a classical cactus graph. So these are not IDs of the problems because it's hard to order the problems based on complexity of which problems. So this is actually the number of problems solved optimally till a given time. So we can solve 169 problems in 500 milliseconds optimally. So that's the precise.
The problem is like randomized starts and finishes.
the problems are somehow randomized. There is some structure in them, as I mentioned. We have a description in the paper precise. So the graphs are not completely random. They are grid maps, but there are specifically placed obstacles, and also the agents are somehow specifically placed, for example, to go against each other and so on. So we have really many types of problems. Okay, so yeah, finally, the original map problem, because I showed you the models where the agent is not allowed to go back to any node, which is not classical multi-agent pathfinding, because it does not allow the agent to go there, then make a space for another agent, and then go back. These models do not support it. So we have a model that actually will be presented at this conference, so the paper is in proceedings, that extends the scheduling model to allow revisits, okay? And the idea is that in SAT, the layered graph corresponds to time slices. And we propose in CP to also use layered model, but now the layers corresponds not to time slices, but to revisits. Okay? So each time we need to go back to some node, we need one more layer so we can go back. So the idea is that now we have a bigger graph and we never go back in that bigger graph because the same node appears at several locations. Okay? Let me show what I mean. So this is a first layer, and if the agent is just moving in the nodes without going back, we don't need anything else. So the agent can move there. But now we need to go back to node 2. So it's not possible in that model to visit the same node again, as I showed before. So we introduce a new layer where we put a copy of all the nodes, and now the agent can go there because it's a different node. So every node is now different, even if this is a return. Right? So in this way, we can model revisits of the same node, and we can still use the same model as I presented before. Right? We just need more layers, but everything else is the same. Okay? The only difference is obviously that now the activities are not just per agent and node, but per agent, node, and layer. This is the activity for visiting the node, and this is the activity for using a given R. Right? So we just use more activities, but it means just a larger graph. And obviously, we introduce activities for transition between the layers. So there's an activity, go from node V3 to node V3 in the next layer, which has a 0 duration, and it allows us to go to the other node, to the other layer, and obviously we set the agent to be in the initial location in the 0 layer, and to be in the final location in the last layer. So it's a big difference. It's now orthogonal to the layers before. So now the layers are defined by revisits. Okay? So the advantage is that if we don't need to use revisits, we don't need that many layers. In the SAT approach, with the layered approach, we need as many layers as the number of time steps. And it's really a difference. Okay? Now the question is, okay, how many layers we need to introduce? Okay? So there's a formula that is described in the paper. The MB is the upper bound for the make span, and Pmin is the length of the shortest path over all the agents. And the explanation of this formula is that, okay, if I have the shortest path, which means obviously without revisits, and if I have the make span, how many times I can revisit the node? Well, it's the number of nodes between the shortest path and the make span, so that's the difference. But obviously, if I want to revisit the node, first I need to leave it, and then I need to go back. So that's why it's divided by 2. And the +1 is just for one revisit or something like this. Okay? So this is the upper bound, and we actually proved that it's not possible to find a better. Okay? So this is the number of layers we need to introduce. So it depends on how we estimate the make span. Okay? So this could be really a huge number. If you are asking how we estimate the make span, well, we can use some of these incomplete algorithms, suboptimal algorithms like push and swap and so on, that will generate plan with a given make span. So we know that this is the upper bound for the make span, and this is calculated easily using the shortest path. Okay? So now the idea is that rather than generating all the layers we need, we can add them again incrementally, right? So we add the layers one by one, and this is the maximum that we need to add to be sure that we have an optimal solution. And now when I'm talking about optimality, I'm talking about maximum optimal solutions, not about sum of costs. Okay? And there are some tricks like we can find the smallest make span and use this make span to estimate the number of layers rather than trying all of them, which leads to suboptimal algorithms. Okay? So this is a comparison. What we did is we encoded this using this logical approach in PyCat, so we can use the numbers there. And this is the algorithm which guarantees optimality, and there's a heuristic version that is suboptimal. And again, this is a number, now it says, number of solved problems, and this is the runtime to which we solve it. So we can see that for simple problems, the sub-based approach is better, but then the CP approach is becoming better. You may say, okay, now they are becoming close to each other, so let's now look what's the advantage of sub over CP. So we say, okay, in CP, we can use distances as numbers. In sub, the best distance is 0, 1, okay? So it's a uniform distances. So what we tried is we generated the problems with different sizes of arcs. Obviously, if all the arcs are of the same size, it's like size 1 in sub. So this means the maximum number. So V is the weight size of the arc. 1 means all the arcs are equal. Right? So we can see that the sub, the PyCat represents sub, is obviously the best one. So if we use problems that are like grid works, where each step takes the same time, sub is better than CP. But if we make the problem more variable, like if we use arcs of different size, then suddenly the CP is becoming better. This is still the sub, okay, and you can see the CP is better. And the larger numbers we use, the larger frame, we can model it in sub, but the numbers must be translated to Boolean variables. Then the CP is more and more better. So somehow this answers the question about the size of domains. So if we have uniform sizes of edges, then sub is better. If we have edges like 1 time unit and 20 time units and 15 time units, the more variations we have, the better the CP is becoming for the sub.
But the heuristic solution is just the fastest, but it doesn't give us...
Well, actually, in this case, I believe it returns optimal solutions, but no guarantee for it. Okay, and yeah, so that's all from me about the reduction-based models and questions.
Another question, how about integer programming? Does it compare?
We tried it for the sub-base-like models, and it was not that good. We did not try it for the scheduling models yet. For the scheduling models, we use the iLog CP optimizer, which is probably one of the best solvers for scheduling, but we did not try MIP for scheduling models. But for the path models, for flow models, we tried it, and it was not. Actually, sub was better if you translate this to sub than MIP. But maybe for scheduling models.
I have a couple of questions. So first, I still didn't get how do you figure out the make span? So you said that to figure out the make span, we need to run another algorithm, but in this case, you should include it in the runtime.
So this is for optimal solutions, but about the make span, yeah, I should say, in CP, we define feasibility of the solution, but you can tell the CP solver optimize some function. So this is what we are doing here. So we have the constraint model, which is fixed, and then we define make span, which is the maximum of times when we reach the goal node, and we ask the solver minimize this. and the solver is running branch and bound inside, but the model is the same. So that's the difference from the SAT, where you need to do it at the SAT level. You need to add the layers. In this case, the layers are not dependent on the make span.
Okay,
The layers are dependent.
So in case of constraint, in case of CP, you do not have to calculate make span beforehand to give it as the initial guess on how many
We need, but
this formula.
in this formula, right? So we need to calculate the make span to estimate the number of layers we need, but this number of layers is not corresponding to make span, it corresponds to...
No, so, I get it. So do we need to calculate this before we apply the CP model?
Yes, yeah, because we need to know the number of layers.
So we need to know the make span.
No, he needs an upper bound on the make span.
I don't need obviously the better value of make span I get, the better value I get here, but I need upper bound for the make span. So I need to be sure that there exists a solution with that make span. So I can use suboptimal algorithm which is fast to calculate it, but the make span might be big one. So when I say make span, I mean the upper bound.
The upper bound. So, and in this experiment, what sort of upper bounds were you using? I mean, like how did you get this?
Yeah,
upper
we
bounds?
get them from push and swap algorithm that
Did-
Ronnie described before. So this is
And
suboptimal
did-
one.
Did you include the runtime of push and swap into your runtime because it's obviously a part of?
Yes, but it's very fast.
Oh, okay. So I mean, like, these runtimes, they include the calculation of
They
this
include
upper
complete
bounds,
they
okay.
include complete solving the problem.
Great.
Actually, there are also some iterations behind. So
And another question: did you have any like figures to compare with the same problems, but for example with another solvers like?
the problem with another solvers is that they are for the classical multi-agent pathfinding. So no distances, if I'm wrong. All edges have distance 1, and that's it.
Yeah,
So-
well, even in this case, for example, if in this case it has no.
So what we did is we represent these other solvers by the PyCat, because in PyCat we can include these numbers and they are translated to this logical formula. So this is somehow representative of the other reduction-based solvers, not search-based solvers.
Yeah,
For search-based
I
solvers,
was-
it's probably more complicated to introduce durations of.
To some of them, yes. To some, yes.
Yeah.
To HTTPS it's hard, to CBS it's relatively easy. It depends on the.
So there is no, I mean, there is no solver that includes these properties. You need to modify the solver. That's what I want to say.
To some extent. There is no implementation yet. But
That's what I mean. Yeah. So
But
there
it-
is no implementation that we can take from somebody, because if we implement it, somebody can say you did not implement it properly. So that's why we cannot compare on these problems directly with other solvers.
No, I mean like on this, even if you have unit costs, like.
Then we can compare.
Yeah. So did you compare what?
Oh yeah. So this is the comparison with the PyCat, because if it's unit cost, it's like the SAT solvers.
No. I mean like, did you compare with with?
Oh, with search, no. In
Yeah.
this work, I believe we did not compare directly with the search.
Because I believe that like in my opinion like I'm not
Yeah,
sure
so
about.
I think I understand the question. So let me elaborate, please. So both of us have done any comparison of the compilation-based approach against the search-based approach. And in general, and this is a generalization, and like any generalization, it has some false positives and false negatives. If the grid is small and very dense, the compilation-based approach works best. And if the grid is very large, then the compilation-based approach in general work not as good. Okay. That would be, I think,
Basic
yeah.
characterization.
So for example, on the Dragon Age maps, they really work well, but on small grids, very, very dense, like CBS would crash, because there's so many constraints, and these approaches work wonderfully.
It's a rough characterization of which one is better. Okay, so there are no more questions about compilation-based approaches. Something interesting about execution.
Thanks, Roman. Good, you stayed. Yeah, and we have new water, even better. Okay, so yeah, I'll just say something about the reduction based. So for me, it's amazing how efficient and strong the SAT solver and CP solvers are today. And this is the second domain that I've worked on, where SAT-based approaches and CP-based approaches are provide like state-of-the-art in some cases. So it's really cool. Okay, good. So from planning to execution, yeah. So I know that we have many people from different countries and there are different idioms. I don't know if the one up there is known in different languages, or we can make plans. And you see the robot and the banana. You can imagine what's happening there, right? Yeah. But still, it's funny to see. So let's look. Okay, it's cliche. Let's walk. Okay, so we can make plans. I'm not showing what happened with the knife and the apple, but so making plans is wonderful, but we all know that when reality comes, some unexpected event occurred. And for example, this is the intersection setting that Roman showed at the beginning as one application. This is from Peter Stone's group on automating an intersection. This is basically also some form of multi-agent pathfinding problem. Agents want to reach different lanes and they don't want to collide. And they've shown that this is much more better than stop signs or traffic lights. But you can imagine that if during execution some of the cars malfunction or slow down a bit, right? Then this would not end up well, right? So when this occurs, or for this case, what is the most important thing to do? So first of all, to know who to blame, right? Actually, and there is actually work on that. Which agent malfunctions to cause this collision? But this is for a joke. What we do want to do is how to react when something changes. So we plan for all the agents, and then something unplanned has happened. This could be a delay or moving to an unplanned location. So what to do? So this is one thing. And the second thing is, given that we know that reality is unpredictable, can we plan upfront in a way that reacts to that in some way? Okay, so I'll talk a little bit about both. And I'll say that so many unplanned events can occur. For simplicity, I will talk only about delays, but other things can occur. So this is one disclaimer. So the unexpected event is agent wanted to go here, and it took him longer than planned. So this is one disclaimer. The second one is, so you could take all this kind of thing and model it with classical uncertainty models, MDPs, BOM-DPs, and all that. The problem is very, very roughly, and I am overgeneralizing, they cannot scale to a large number of agents. And we want to scale to a large number of agents. Okay, so just to clarify what do I mean by an unexpected delay event. So here says two drones. Each one of them wants to go to its goal. If you look closely, it's very different from the picky mouse example. These are drones, it's much more cool. And you can see, and this is the original plan. You can see this is a valid plan, right? So it will go here, and let me show you. So it will go here, and then the red agent will wait, and the blue agent will move, and then they will get to the goal. Okay, so good plan, right? It should work. Okay, but then we start running it, and at time step 2, the blue agent, which was supposed to pass first to 3, it got delayed, and it didn't get to B. Okay, so now all its plan, right, it got pushed a little bit aside. Okay, so now if we continue the plan as is, you can see what will happen, right? At time step 4, we will have a potential collision, and we don't want that. Okay, so now the question is what to do. We are now at time step 2. We can say if we will continue the plan, we will collide at time step 4. What would we do? So what we wouldn't want to create a collision. Okay, so very, very, very roughly, very, very overgeneralizing, we have two options. We can either repair the current plan, or we can either replan from scratch. And the simplest way to repair the current plan is, we are here, right? Here. So agent red will wait. So just wait a second. So it took its plan and added another wait action. And this would repair the plan. We would get back to the same setting. But of course, this is not very efficient. If you look at, and where's the? Yeah. So I'm focusing on this option, the wait option. So we reach here. The original plan was for the blue agent to go to C, so to be first, but it got delayed. So waiting would mean agent red you keep wait, and you even wait one step longer. So this is what we will have. Okay? Wait, 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 see. And allowing the blue agent to come first. Okay, of course this is inefficient. Right? So this is that being stuck. So the other plan is, if you're here, okay, let's replan. I'm here now. You know what? Let's have the red one pass first. Okay, and this will be faster. Okay, so why is replan not the best option always?
It's more time.
More time. Planning takes time. Another reason?
Well, they have to communicate the plan.
Exactly. You need to send them something, so you need some communication skill. So these are both limitations. Okay, so why shouldn't we always repair? If replan is so horrible, why not always repair? This example is here. Easy questions now. Why repair is not always the best option?
Takes longer.
Look, takes longer, right? Again, a simple question. I'll get to the harder one maybe later. Okay, so very, very simple. Repairing is fast compute, fewer messages, no communication, but solution quality may be bad. Replanning, better solution quality, but you need to synchronize and it's hard to compute. Okay, but this is not the only question that we have when we are talking about planning and execution. I will say also that there aren't a lot of work on planning and execution for multi-agent pathfinding. So I will leave you at the end with more questions than answers, but there will be some answers also. Okay, so this is one dilemma, repair or replan, but it's not the only dilemma. The second dilemma is when to do it. So we observed now the delay, but it's not necessarily clear if you want to handle it now or maybe wait a bit. Okay, because if you look at it now, then there is a potential collision here, right? But you know, if I will do nothing and continue, who knows what will happen? Maybe there will be an additional delay, and we won't need to do anything. Very, 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 very roughly, you can say that there is an eager approach. Whenever you see a delay, handle it. There's a lazy approach. Let's wait when it happens. And you could also look at somewhere in the middle where you will act immediately, but only if the delay caused or may cause a potential conflict. Because it might be the case that there is a delay, but you know it's still okay. You can still continue. There will be no collision. So there are three options, and now so we had repair and replan, and we had these three options. So actually we have 6 possible configurations, right? So we have you can repair or replan, and you can be lazy, reasonable, or eager, right? So there are 6 possibilities at least. Actually, I put here not available for being lazy and repair. Can anyone see why lazy and repair is not a good combination? So lazy means I won't do anything until I'm a minute before the collision, and repair meaning I will wait and let the other guys continue their plan.
It can be too late to do anything about it.
It could be too late, that's good. Let's take it to the extreme. Let's say that I'm the agent that should have waited. It didn't, and now I'm about to collide with the other agent that comes up front of me. If I'm repairing, that means I'm waiting for the other agent. But he would not be able to continue. So this is not completed. I might wait indefinitely.
But if, like in this example here, agent B was delayed, and then if we waited for example, agent 3 to get to position 3, it could be that agent A was also delayed.
Yeah.
So it's kind of like a lazy repair strategy.
So again, lazy repair, it may help in some cases, but there are cases where you want to help. I'm not saying I'm saying that it's not. If you use it, you might end up with a deadlock.
I don't know. I just understood that it's not an option. So
yeah, okay. It's an option that might lead to a deadlock. You're right. It's a better. I should have rephrased it. Okay, but there's also a third question. Let's say we decide to do something. The issue of communication was raised. When should the agent communicate? And here, actually, is a very neat solution by Hangma et al. From USC, which is a protocol of when to communicate that provides minimal communication, but still completeness of solution. So it gets as input a multi-agent pathfinding plan. It starts executing, sometimes get delayed, and it sends the minimal amount of messages so that at the end, all agents would reach the goal. Okay? Very neat, very simple. I will explain it now. Okay, so here's the MCP protocol. So the idea is like this. First, get a plan. How do we get a plan for multi-agent pathfinding? At this stage of the tutorial, you should know many options. Let's say we run one of them. Okay, so this is the plan. Now, I look at the locations where agents may collide in. So in this case, what are the locations where the agent where conflicts may occur in practice? So the plan is valid, right? They're not colliding if everything will go according to plan. But if something happens, where might they collide? S2 and G2. Very good, right? So this place, right? Because if this guy will get delayed, it will collide with this guy and G2. Right? All the locations. And now we look at the precedence relation between them. So what I mean by that is that according to the original plan, the blue agent reaches S2 first. After it, the red agent should reach it, and after that, the blue agent will reach it again. Similarly, the red G2 is reached first by the red agent, and then it reached by the blue agent. So we would like to preserve this relation. So we model this. We have these edges, and this is easy to compute. And now we only want to preserve this ordering. So what MCP does is that it repairs, so it lets the other agent wait only if it's about to pass one of these possible joint locations or possible conflicting locations. So, and this also implies which messages to send. So when the blue agent leaves S2, only then it broadcasts I left S2. This is the only message it needs to. So when it leaves the joint locations, it sends a message. And why does that? Because the red agent, for example, would never enter S2 before it got a message from the blue agent. So when it will repair, it will only repair if it reached S1, it's about to enter S2, and it didn't get this message. If this is the case, it will wait here until it got the message. Similarly, agent blue, or the blue agent, would never enter G2 before it got a message from the red agent that G2 is here. Yes, question?
Is this a lazy approach?
So this is not the lazy approach because, or this is a variant of the lazy approach because, for example, maybe he is here and he is not yet. This is not a good example. Let's look at this example. Okay, let's say the red agent gets delayed here, gets delayed at S2 for like many time steps. Okay. So the blue agent reaches G2. It can go into G2, right? Because the red agent is in S2. So it could go in. The lazy approach will tell it go, enter G2. It's okay. Because the lazy only repairs when it's about to reach a collision. Here there is no collision, but still, according to MCP, it will wait here until the red agent will finish G2. Okay, so this is a slight difference, but it's an important one. Okay. Yes, questions? Okay, good. Okay, so this is a repair. I will also mention that this is the classical MCP, but actually, again, Ma et al. In a different paper, they introduced something that's related. Okay, they didn't formulate in this context, but I will anyhow. So repair can be not only wait. Repair can also be I was delayed. Let's speed up a bit. But then the question of I can't speed up to infinity, right? So I need to reason about can I speed up enough in order to go back to the original plan. And what they propose to do, and I'm not showing it here in details, is that take this plan and now add all the precedent constraints between the steps. Okay, so there is the one step after the other precedent relation, and there is also the relation between that we talked about before. That this needs to enter S2 before this one. And now this, together with the maximum velocity constraint, you can create a simple temporal network on that and solve it. And the solution for that would be how much or if there is a solution, then I can repair. If there is no solution, I can't repair, I need to replan. And this is also mentioned that I gave the introduction that they didn't aim for this specifically because their work was actually more general in the sense that they also implied how to do multi-agent pathfinding with any kinematic constraints, which also has the same property. Okay, good. So this was this, label each engine. Okay, and what's nice is that you can do that in polytime. It's important. So once we have this simple temporal network, which was created with the plan and the maximum velocity constraint, I can get solution in polytime, which is wonderful. It's not hard to do. Questions? Good. Okay. So this was a very, very brief discussion of more or less all that has been done on reaction in this context of multi-agent pathfinding, which is too little in my view. So I think there's a lot of cool things to do. I will now talk about the other part, which is I know that delays might occur, how can I plan upfront to take this into account? Okay. So I think that there are three approaches. One of them is let's find a plan whose minimal expected cost who has a good expected cost to it. So I take some knowledge about delay probabilities and then compute some expectation. And this was done a little bit by Michael at a paper a year ago. The other approach is I can try to find a plan that's executable with high probability. And this was done by a variant of the M-star algorithm, which is called UM-star. I will talk a little bit about it later. And the third approach is to find a plan that's robust to a fixed number of changes. So this will be a plan that I'm following, and I will be able to follow it even if up to k delays occur. And this ties back to the robustness that Roman talked about at the beginning of the tutorial. Okay. Any questions so far? Okay, so I won't elaborate on all three because we don't have enough time, but I will say this. So in the first one, the expectation cost. So do you see the asterisk there? That's because their algorithm, which was good, I don't know, it was based on CBS. It do not guarantee anything about the expectation. It's an approximation of the expectation, and the reason for that is it turns out that computing the expected cost of a plan given delay probabilities is not an easy problem. Okay, so it wasn't. So there is no known proof of NP-hardness, but it looks at least it looks like this is the case, or it's not trivial. So even if you have a plan and you have delay probabilities, getting the probability that there will be a delay is not trivial to do. So now let's talk about UM-star. So here is an illustration about how UM-star works. So again, the purpose of UM-star is the second option there, which is get me a plan whose likelihood of getting a collision is small. And what it does is that for every state, it also keeps track about the last sequence of state where the agent was before. And for each of these states, there is a score, a likely probability of what is the probability that the agent is there at that time. And this allows computing the likelihood of, or at least approximating the likelihood of having a collision. And then based on that, this plugs in the M-star algorithm and works reasonably well. There is also a CBS version for that. Okay. I'm missing some slides here, but never mind. Okay, so I want
one question.
Yes.
If you go back,
yes.
is that the probability? Was it on the tail or on the front of the?
Yeah. Okay. So it's on the plan.
Okay. So that's a delay, of course. Yes. Yeah.
So when you compute the delay, we compute over all possible locations, all possible configuration where it might be, and then gets us. Okay. Yes. And the third option, which is the one of K-robust, then if you want to hear more about how to get a solution that's robust to K steps, so there is a wonderful poster 2 days from now at AMAS, so go and hear it. But there is a solution to K-robust also based on a compilation approach, which Roman has done, and also with CBS approach, which is also done. So there is a solution for the robustness option. Yes. Okay. So this is all I have time to say about planning and execution. But I think it's intended this way because it's really an understudied topic in multi-node pathing, and I think it makes sense now to invest efforts in this aspect because this is crucial to applications. What you've shown is that the first dilemma is, do we want to repair or replan? And there are also several options to repair. Second dilemma, when to do it. You can do the eager, reasonable, or doing the lazy, or even the minimal communication policy that I've shown. And the third one is to a priori do some planning to avoid either avoid collisions in some probability or get some expected guarantees on that. But there are many open challenges. To list several of them is how do we consider solution quality? So we need some kind of, because we have two parameters. We have the risk of collision and we have the solution cost. And it's not directly clear if they are directly comparable. So how much time does it cost to break your robot? that depends on how complex the robot is, right? So this is one challenge, and I think this opens up the way to having some multi-objective optimization algorithms into the loop. So this is one open challenge. The other one is, so there is a body of work on contingent and conformant planning, which is the planning where there is some non-determinism, and I either can detect it or I cannot detect it. So how to do the mapping between these two domains, two types of problems, and also lifelong planning. There is a little bit of work on that, but the idea is that we do some initial planning and we improve the plan throughout work, throughout the execution of the algorithm. This is another topic that's of interest. Yes. Questions so far? Good. Okay. So, in the last 2.5 minutes, I will say a little bit about challenge and conclusion. Okay. So, why I like to work on multi pathfinding? This is how I like to conclude this talk. So, first of all, it's a real-world application. Okay. There is at least one representative here of what has it, and I think more. So it's real world, which is nice. It's a very challenging multi-agent problem, so that's also fun to work on. And it's also, from the search guy perspective, it's a very challenging search problem. Also interesting is that we've shown in this tutorial, I think at least 10 approaches. So search-based approach and A star, non-A star, complete, not complete, CBS, ICTS, A star, and reduction-based approaches, CP, SAT, at least 5 models I think Roman covered. So there are many approaches, but it's not really clear which one is dominant, and there is no dominant approaches so far. So by working on multi-pathfinding, you are exposed to many different fields, and it's really interesting to see the interplay between them. When does one approach best the other? So we talked about that, and in every planning world, execution differs from planning. But in multi-agent planning, I think it's even more critical because you're integrating between several robots. So beyond the deficiencies of the single robot, there is a deficiency about the interaction between them. So it's clear that some meaningful thing to do about the execution and planning. It's crucial to make these things work. Okay, and there is a lot more left to do. Beyond the algorithmic part, which I think we've covered for the specific multi-agent pathfinding, I want to highlight several others that I think are worth mentioning. And one of them, which there is a little bit of work on, but not a lot, is that so far we assume that the agents will do what you tell them. So you'll tell each agent, so you can imagine an autonomous vehicle scenario. Every person wakes up in the morning, and some central controller tells the car, each person, how its car will drive to work. You know that this will happen. Very quickly there will be a black market of people that are hacking it and trying to get faster to their goal. Because in this example, you can see A wants to reach A and B wants to reach B. What is the optimal solution? One of them needs to yield, right? One of them will pass through the fast lane, and the other one will go first. Who here would want to be agent B? No one, right? Okay, so there needs to be some work on incentive design or some mechanism design work on how to make the agent follow the optimal plan. And this becomes even more complex if the agent is human, so we need to reason about how human behave, or maybe the agent is some adversary. And there is a little bit of work on self-interested agents by Nayata, and also, so we didn't get to the combinatorial auction setting, but there is also work on how to create strategy proof mechanisms for multi-agent pathfinding. And just to highlight it, what's here is one very preliminary work on self-interested agents. And what you can see here is that, so black is the total sum of, it's the distance traveled. And now, and if each agent is selfish, you can see that the line is very high meaning very slow. But if you add some tax-paying capability, you can get to much lower overall. So this is some taxation mechanism, and you can reduce the overall planning driving distance with slightly paying more. So this will be interesting how to create that. So this is one challenge, I think, how to move to non-cooperative agents. Another one is applying it to real problems, robotics. So in robots you have kinematic constraint, uncertainty is a key, you must reason about it. There is a continuous configuration space, so we talk only about discrete things, how to make how to work in a continuous space, and also the emotion is not discrete, so how to handle that, and there is some work on that by Constantine, which is there, we can talk to him also. And also, so how does multi-pathfinding relates to traffic management? So I know that the group of Peter Stone and Ronnie Sharon is working on that. In traffic management, it's not exactly the same because it's not discrete anymore. There is flow-based mechanism because two agents can be together in the same highway. It'll just take longer. So how to do that? So this is also interesting, and scaling is an issue also. More work also on task allocation, which agent will do what. Also some work on that. I'm putting this not just so you know that if you are interested in that line, you can look at the slide and follow that up with references. And there's also the online setting where agents come and go, so this is also interesting. Last thing I want to say is that multi-field pathfinding, especially since we are exploring in AMAS, is just a special case of the more general multi-field planning. And it's really interesting to see if there is a way to make this relation tighter. Because multi-field planning, again, this is math. Multi-field planning as opposed to pathfinding. So, of course, pathfinding is one form of planning, but planning is like a little bit more complex. Because in planning, the agents can also help one another. While in pathfinding, agents can only block their way. And in general multi-field planning, there are many models, a lot of literature, a lot of work on uncertainty, but if you look at work on multi-field planning, mostly they don't scale to a large number of agents. On the other hand, multi-field pathfinding, this is a relatively younger field. I think you'll not find a lot more if you go back 10, 12, 13 years ago. And in the most work are relatively restricted models, but it scales very well, as you've seen, like to hundreds of agents. So it will be interesting to somehow cross-fertilize between the fields. Yeah, and I think that's it. Here, I'll skip that. I think this is a video of the chemistry model, because I think multi-field pathfinding is more than just robots and traffic. There are various domains, and Roman mentioned the chemistry lab on chip setting, so you can see how it works in the background while I open for questions. Okay. So we won't see it, but it will be online. Okay, thanks for coming.
Do you have any recommendations for presentations that will be held the following days that we should attend if we are interested in these topics?
Good question. So first of all, there is Roman's work, which was presented. It's a full paper, right?
On the scheduling, yeah.
Yes. So on how do you apply scheduling modeling to? So that's one. There's also, so I have a poster, but let me do this. I will go over the schedule now and mark what's relevant, and then I will just post it somewhere or send it. Yeah, how will I communicate?
You can put it on the Hoover.
Hoover, good. I don't know how, but I will figure out. Okay, so it will be on Hoover. Yeah.
I have my paper was not accepted to the main robotics track of the conference, but we have a poster about kind of the same problem, but slightly different approach, which is more often used in robotics when you just assign the priorities and they plan one by one. So if you're interested, you can come to this poster as well. So there won't be any formal presentation.
Yeah. Before I take another question, I want to ask two favors. One of them, I need to prove to my wife that I'm working. So if you're willing, I would like to take a picture and then post it on my website. So that's okay. It would be great. If you're not, then please hide now. Roman, do you want to?
Yeah, sure.
Okay. So look serious. Okay, good. And thank you for that. And the second thing is, so if you're willing, and then no pressure, I'll to write your name and email so I know that you're interested, and then I can send you stuff. So that's on that, not more than this week, but a list of papers and the presentation. If you want to put it online, but I'll just send it to you by push. Then I'll just put my laptop here with some spreadsheet, and you can just put your name and email. Again, if you don't feel comfortable with that, that's also okay. No worries. Yes, more questions.
Yeah, so just another question is that on these pathfinding agents, typically it's the discretization of some grid, and then agents move into the grid. Recently, a colleague of mine had a problem where she's working with a set of drones, and these drones have to fly to some locations within time constraints. but the problems with the drone mechanics are not like it's not easy to model them as these grids because they have some particular movement how these
Yeah.
machines can work. So I'm just interested in is there work to tackle these kind of problems?
Yes, yes. Okay. So I have two answers for two and a half. Okay, the half is Dr. Constantine. I think he worked on that a little bit, so or not a little bit. So what to talk to him, but here's the two that I can expand more. So there is work by Hangma on doing multi-input pathfinding with kinematic constraints. And what they did is that they first solved the problem in a discrete way. So and then over that impose the kinematic constraint by adding the temporal constraint of okay, these motions can be done with the kinematic constraints. Only it takes it this at that time, and then they schedule the actions to conform with that.
So they make like a rough plan and then they make it more precise.
Yes. So this is, there's also work by Stuttervant and Walker on starting with a very, very rough plan, like with very like small number of actions, and then add more complex actions. So this is one answer. The second one is, so there is, in general, in robotics, there is the search-based approach where by Likachev's group in CMU, that they compute upfront motion primitives, or that go like this, go like this, go like this, and then, so there is the grid world, but the motion is not like up, down, go right, but like from here, you can go to the two up and one diagonal, something like that.
Like chess.
Yes, yeah, exactly, yes. So that's another approach, that's what we have to check. Yes?
Can you make the connection to multi-agent Markov decision process? Where
Yeah. So I again two answers. First of all, I think the connection is not strong enough, but so you could look, so you could solve at least the delay probabilities part with the multi-agent MDPs, but usually the MDP solvers are not very scalable. So most will go for 3, 4, 6, 9 agents at top. And the reason for that is to make them scale, you need to define to them which states they should interact with. There is some work by Manuel Valosa and others. And the problem is that in multi-agent pathfinding in general, every state you can collide with, because every agent can reach it. The agent can collide in many places. So that's why it's not trivial to do this connection. Is it impossible? I think it's like, I think more work can tie the knots together, but this is mostly scale. That's the missing part.